Well, then, why don't we go ahead and get started here? Good morning, afternoon, or evening, everybody. This is your host, Jennifer Brennan. Welcome to day one of the Fundamentals to Use Hyperspectral and Thermal NASA Earth Observation Data Workshop. I'll kick off today's workshop with some logistics and housekeeping information. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or have any questions, rather than to raise your hand, please enter those into the Q&A panel or the chat, and you should find that located on the right side of your screen. If you do not see the Q&A panel, click on the three dots at the bottom of your screen to pull up your panel options. You can then insert add a check mark next to the Q&A panel. Okay. Let's see. A quick word about the chat. Participants will have the capability to chat with the hosts and the presenters, but not with other participants. So again, if you have any questions, please enter those into the Q&A panel on the right side of your screen rather than a chat. If you're having any technical issues, please feel free to reach out to me, Jennifer Brennan, or my co-host, Joseph Smith, and we'll try to address those WebEx issues with you privately. Today's workshop is being recorded. When the recordings are ready, I will follow up with a link to the webbook, which includes links to all of the presentations from this afternoon's and tomorrow's workshop as well, and also the recording link for today's event. We have multiple speakers from the NASA's EMIT, ECOSTRESS, and PACE science teams, as well as subject matter experts from NASA's Land Processes Distributed Active Archive Center, or LPDAC, here with us today. And so before I toss it off to Africa for the introduction, what I'd like to do is just make one final note about the Q&A sessions. There'll be a built-in Q&A session, like pretty short after each talk. And I think after the third talk, so there's 5 minutes after each talk. And after the third talk, there'll be a 15-minute Q&A session. But if our panelists and speakers are not able to address all of your questions during the Q&A periods that are allotted, they'll be able to follow up with you offline. So with that, what I'd like to do now is stop sharing my screen and introduce today's first speaker, Dr. Africa Flores Anderson. Africa, so with that, let me go ahead and stop sharing my screen and toss it over to you. Alrighty.
Thank you so much, Jennifer.
You're quite welcome. All right.
Welcome, everyone. Thank you so much for joining today. We have assembled a multidisciplinary team to provide this webinar that is trying to bring together the latest and greatest measurements from NASA. Just to briefly introduce the team, we have multiple NASA centers participating here. And I would like to briefly mention and introduce the missions applications leads for ECOSTRESS and EMIT, Christine Lee and Dana Chadwick. They will be the first presenting today. And we also have the science team members for EMIT and ECOSTRESS, David Thompson, Anthony Hooley, that will provide the fundamentals for the hyperspectral measurements in the visible and shortwave infrared part of the spectrum, and thermal measurements as well. We also have the applications team lead for PACE, Morgan McKibben from NASA Goddard, and subject matter experts from Marshall, that includes Emil Charrington and myself, and Aya Linkwitz from Goddard, that are going to go through tutorials and hands-on materials to use these different data sets. We are going to focus on 3 sensor datasets, EMIT, ECOSTRESS, and PACE, and I'm going to be repeating these throughout this brief introduction. And if I haven't mentioned, we also have remote sensing scientists and subject matter experts from NASA LPDAC that deal directly with all the land surface measurements that are coming from some of the NASA missions. So the goals for this event are first to understand the fundamentals of imaging spectroscopy, that is acquiring very high spectral resolution data sets in the visible to shortwave infrared part of the electromagnetic spectrum, and also thermal measurements. We are going to use these datasets through different tutorials, hands-on tutorials, and the goal of all of this is for you to have your hands into the data, create some data products. We are going to be working with level 2 datasets, and we also want to provide all the background about how these measurements are acquired, pre-processed to get to your hands, and then actually dig into the data. And these are using some of the newest and latest measurements that NASA has for this part of the electromagnetic spectrum. So what to expect from this today webinar? The first day is going to be mostly theory. First, we are going to have like a big picture of how you can use these data measurements to take informed decisions. So we are going to hear from the missions applications leads from these different missions that I have already mentioned. EMIT and ECOSTRESS are instruments that are in the International Space Station, and we have the missions applications list that will provide examples of the applications of these datasets and the decisions that can be informed through the use of these datasets. And the same for PACE. And then we will go through the fundamentals of imaging spectroscopy for VSWIR measurements, that is referring to visual to shortwave infrared measurements, and very narrow bands, consecutive bands that are some of the newest and latest technology that we have available and that is available for the whole world now. And also we have the fundamentals of thermal measurements. In this case, we are going to be working with ECOSTRESS. At the end of the day today, we will go through some to make sure that all of you have your cloud environment set up. We are going to use two platforms, Openscapes and Google Earth Engine. So we will make sure that you have your environments ready. The second day, and if you haven't registered for the second day, please do. And there are two links for registration. And we noticed that there is more participants on the first day, and it just be a matter that you also need to register for the second day. The second day, we will go through the tutorials. The first part, we will access level 2 land surface temperature from ECOSTRESS. This is a multispectral dataset that we will explore and process and visualize. Then we will go through the fundamentals of the EMIT level 2 surface reflectance data, and then we will also explore a Jupyter notebook that goes through finding coincident data from EMIT and ECOSTRESS. And all of that will be, and then we will go through the PACE level 2 land surface reflectance product, how to access it, process it, visualize it, and manipulate it. All of that will be done through Jupyter notebooks in using the Openscapes platform. That will be based on Python. And then we will go through Google Earth Engine, and we will work with PACE, EMIT datasets, level 2 and level 3. And that's how we have assembled these 2 days of work. Is like a fast course on the fundamentals of imaging spectroscopy for the VSWIR and thermal measurements with hands-on materials. And just to highlight again the missions that we will deal with, we will be working with data from ECOSTRESS, which are the thermal measurements. This is a sensor in the International Space Station, and also with EMIT datasets, which is also on the International Space Station. And then we will also work with PACE OSI Ocean Color Instrument on the PACE mission, and that is its own satellite. Our colleagues at LPDAC have also created a webbook with the presentations and the Jupyter notebooks and the tutorials, everything hyperlinked as much as we can. We are updating this constantly. So if you don't see everything available here in terms of the presentation or the Jupyter notebook, in this moment, it will be available there. So you can have this resource throughout the webinar to access the presentations, to access the tutorials. So thank you so much. We expect an active event. We will do our best to address all the questions you have. We recognize that there is a high level of participation, so we may not be able to answer all the questions, but we will collect all of them and ensure that all the responses are provided after the event in case we are not able to answer all of your questions. And that's all. Would like to check if Jennifer has additional remarks before we start with the presentations.
No, I have nothing further, except I did see a message in the chat that some participants are unable to access David Thompson's presentation. So David, if you wouldn't mind perhaps adjusting permissions there, that would be wonderful. Thanks so much, everybody.
Thank you so much.
All right, and with that, let me pull up the agenda. So we are going to continue. We're a little bit early. Are you ready to move forward to the first set of presentations? Africa?
Yes, we have, I see Christine and
yes, so with that, we are going to move to our first set of speakers from the introduction for an introduction to EMIT and ECOSTRESS applications. And so with us today, we have Dr. Christine Lee and Dr. Dana Chadwick. And so I turn it over to you to kick us off. All right, thanks so much.
Hey, I'm just getting things going. Can everyone hear me and see my screen? I may need an audio cue because I can't see.
I can hear you and I can see your screen, and it is currently in slideshow mode, so perfect. Thank you.
Awesome. Thank you. Hey, everyone. My name is Christine. I'm a scientist at JPL in the Water and Ecosystems Group, and I work with the ECOSTRESS team, and in particular, Madeline Pascalini-Campbell, who is the applications lead for ECOSTRESS. And together, along with the ECOSTRESS team, we have been working to maximize the impact of science for society through mission applications. And I'm excited to share with you some of the ways in which we have done that, as well as provide an intro to the project. And so what I hope to convey to you in this presentation is how mission applications in tandem with the science teams have really been able to increase the benefit of our different NASA missions on society by expanding some of the beyond the prime mission goals of our satellite and other spaceborne projects, how we have been working to be responsive, providing responsive science for society and focusing on actionable and timely information, as well as exploring opportunities to work across missions a bit more to amplify benefits to the broader community and to our partners, such as is the case for workshops such as these that are exploring different types of measurements from different missions and using them together to address joint science and application interest areas. And so I'm going to talk a bit about the ECOSTRESS experience. And so ECOSTRESS is a NASA project that was selected in 2014 and was launched and instrumented onto the International Space Station in 2018. This was a cost-capped mission at about $30 million and measures surface temperature in 5 different bands across the 8 to 12 micron wavelength range. And some of the unique aspects of the ECOSTRESS mission is that we provide 70-meter spatial resolution data at about a weekly revisit for our sampling sites, which includes the continental United States and other locations around the world. And our primary standard data products that you can see listed here include the calibrated radiance, geolocation, land surface temperature and emissivity, ET, water use efficiency, and the evaporative stress index. So the prime mission goals for ECOSTRESS are to explore these three primary science and application questions, namely understanding how plants respond to changing water availability, leveraging the unique precessing orbit on the International Space Station to look at ET at different times of day and how that relates to vegetation growth and condition. And then in our third area, we're looking at how we can better leverage ET measurements to support agricultural water use and decision making. So to expand on the way that ECOSTRESS can support societal applications, we initiated an early adopters program. This was a very grassroots effort to provide a venue for scientists and application scientists to come together and learn from each other different ways that ECOSTRESS data can be used. Often, again, expanding beyond some of those primary science questions that were listed in the slides previously. The early adopters program had over 300 participants. We consider it now the community of practice since we've been in operations for a while. And the goal of the early adopters program was really to listen to the science and applications community, understand challenges that they may have working with ECOSTRESS data, and then use that feedback to inform the development of new community tools in partnership with the DAC, as well as to incorporate improvements to the standard data products that is provided through the mission, as well as to expand upon new application areas and impacts. And so this might include providing ways for greater collaboration with public and private entities. And so across the bottom are a snapshot of different organizations that we've been able to have the good fortune to work with that span public, private sectors, different levels of U.S. federal government, state government, and so forth. So as I mentioned previously, part of the core mission of ECOSTRESS is to advance agricultural science use cases and applications. And this is largely done through the standard production of the ET product, which is a measure of plant water use, and to help identify ways in which that ECOSTRESS ET product can be used to optimize irrigation strategies, while maintaining crop yields. And so in this panel, you can see the level of detail that can be provided via ECOSTRESS data, which allows us to resolve estimates of ET at field scale, which has been shown to be very relevant for our agricultural end users. For example, I'll show this example in terms of irrigation optimization. We learned that a private company based in California has been using ECOSTRESS surface temperature to help produce one of their standard products, which is field-by-field evapotranspiration over 3 million acres in the Central Valley, and that their data are then utilized by a number of groundwater sustainability agencies and irrigation districts across California to support water management, regulatory compliance, and other decision support areas relevant to California's Sustainable Groundwater Management Act implementation. And so this is one example of a private company utilizing ECOSTRESS data. We've also been exploring wildfire applications. And so in this example, we're just briefly summarizing areas in which ECOSTRESS can be used for understanding pre-fire vegetation stress. So in the upper left is an example of ECOSTRESS evapotranspiration leading up to the Eaton fire. And then we can also use ECOSTRESS data to understand wildfire recovery and support vegetation mapping in a more of a post-fire environment. And then on the right-hand side is a animation of the evolution of an active wildfire perimeter that we can use ECOSTRESS surface temperature or radiance data to develop as well. Another application area that we've been growing into, or that we are supporting, is related to critical minerals and energy security. And so ECOSTRESS can be used to assess mineral classes such as sulfates, which can be used, whose presence can be used alongside other minerals to indicate the potential for other relevant mineral deposits. That we provide an example of here. We also have learned that our broader community is using ECOSTRESS to detect hydrothermal features as well. So urban resilience is another area that our community has been able to really leverage ECOSTRESS data to expand upon. And so this is an example of the ECOSTRESS team presenting to the Department of Natural Resources Agency for the state of California. This was something that they were interested in learning more about because extreme heat is definitely a priority area for the state of California, as well as many other areas and in urban regions. And so here, Anamika Srivastava was presenting on some recent work looking at the urban heat island effect in and across LA County to our partners at the state. We have also been leveraging ECOSTRESS 70-meter data to look at coastal resources. So here are a couple of examples using that 70-meter surface temperature information over aquatic regions to better understand the status of aquaculture condition for small-scale fisheries, as well as for looking at healthy coral ecosystems, which could be highly relevant to supporting coastal resources and tourism economies. Just another quick example of just the level of detail that we can get with that higher spatial resolution surface temperature information over coastal zones. And if we could do a deeper dive into aquaculture opportunity sites, that may help us inform how to better understand conditions associated with maintaining aquaculture sites. And then next, I wanted to provide a little bit more information on how we have been providing products that are actionable and timely for Urban Heat Island first. And so in this first example, I wanted to highlight work that Glenn Hulley, which you will hear from shortly, has been working with partners at the City of LA to utilize ECOSTRESS data for heat wave mitigation projects and to secure funding for urban resilience projects. And so in the lower right is an example of utilizing ECOSTRESS data to look at the temperature benefits of applying cool paint technologies on different roads. And this was an image that then allowed the City of LA to secure another $8 million in funding for other urban resilience projects. In the lower left, I just wanted to highlight that this information continues to be extremely relevant, not just in the US, but across the world, to map the impacts of urban heat waves. And so particularly in the summers, we see a continued uptick in the use of ECOSTRESS surface temperature information to help detect the effects of these heat waves across cities. Another example of using NASA data, so ECOSTRESS and using Landsat together. Here's an example of a project out of Marshall that was looking at the city of Clarksville, Tennessee, and using a combination of ECOSTRESS and Landsat to generate a time series of nighttime and daytime land surface temperatures that allowed them to reveal patterns in urban temperature trends. And this work was done in collaboration with the city of Clarksville and the Tennessee Urban Forestry Council. So in my remaining slides, I was going to highlight a bit more about the use of ECOSTRESS data in the wildfires domain. And we've been collaborating with a organization. It's a private entity called Stantec, and they've been exploring various ways in which remote sensing can support their clients all around the world. It's a company that has over 30,000 employees. And we recently learned that they were using ECOSTRESS data to help them understand increased wildfire risk by looking at ESI anomalies. And so here's a quick example of a figure that they developed to look at trends in anomalies in ESI leading up to some of the LA wildfire burn areas. And then here I wanted to emphasize a cross-mission collaboration example for wildfires in which we've been working with San Diego State University across EMIT and ECOSTRESS teams to develop improved burn severity maps. And so here's an example of leveraging unique information across multiple missions. In this case, ECOSTRESS and EMIT to improve DMBR predictions and to characterize pre-fire vegetation states and how that informs the prediction of burn severity. So this is work that is being led by Megan Ward, a student at SDSU, along with many others. And so here's a quick example of the produced DNBR maps that leverage both ECOSTRESS and EMIT data. And I wanted to note here that because of the way the random forest model was set up, we could consider and expanding and building on a multi-mission collaboration, we could consider other vegetation condition products as well that could improve the performance of the DMBR model. And then starting to wrap up, I mentioned previously that ECOSTRESS could be used to support critical mineral mapping. And this is even more so the case when thermal and imaging spectroscopy in the visible to shortwave infrared are considered together. And an example of this is high-test and AVRIS and master instruments being flown across the western U.S. to develop highly detailed critical mineral maps, and this is in connection with the USGS for the GEM-X campaign. And then lastly, I wanted to note this report that was developed for JPL. This is an example of us also walking the walk in terms of utilizing Earth observations for decision making. And so this was a report that was developed to inform, understand environmental risks, infrastructure vulnerabilities, and strategic adaptation opportunities for JPL, its surrounding areas, and LA County more generally, related to future risks for environmental conditions. And so this leverages, again, multiple NASA integrated models and analysis projects, various NASA satellite projects and products, as well as NASA airborne data to help characterize these infrastructure risks as well. And so with that, I'm going to close, and hopefully I was able to share some relevant information related to how ECOSTRESS data can be used to support societal applications in science for the broader community. Thank you so much. I don't know if we are doing questions now, or
We do have, yes, we do have some questions. Africa, did you want me to read those aloud or do you want to tackle that?
No, you can go ahead. I have been trying to assign, but I think that we have time to address them.
Okay, great. So it looks like, let's see, 1:32. The next week, we're actually ahead of schedule. So one of the questions is, it seemed that EcoStress is not available on GE. Is there a plan to make it available on Google Earth Engine?
Thank you for that question. We would love to make or have EcoStress become available on Google Earth Engine, and hopefully continuing those discussions with Africa and Emil. There is some interest from the Earth Engine team to explore the inclusion of EcoStress. I don't know if I can ask that person a follow-up question, but if there are particular products that you would like to see from the EcoStress mission that would that we might be able to prioritize in some of those discussions, please feel free to reach out to us and share that information.
Sure. I think that would be fine if the webinar participant wanted to provide additional details regarding specific products in the Q&A or the chat. That would be great. And then the next question is, how can EcoStress data be used to monitor agri drought?
EcoStress data can definitely be used to monitor agri drought, but I'm happy to have a separate conversation with you so that I can better understand what products might be most relevant to your region. But again, 70-meter spatial resolution, approximately weekly. It does vary, but approximately weekly overpass depending on what area we're discussing. And so, and if there's any interest in looking at changes in the diurnal variability of ET in your application, that could also be something that is explored as well.
Well, thank you very much, Christine. And, you know, I will be sending the Q&A and the chat logs to all of our subject matter experts and panelists within this workshop. So our speakers will definitely be able to follow up with you offline and have a longer conversation if needed. So the next question, I'm going to actually skip up to the chat for those questions that do not appear in the Q&A. The first question is, and we may not know the answer to this yet, but what is the fate of these missions based on the NASA cuts?
Well, EcoStress is going to be, as I understand, is going to be operating as long as the ISS is operating. So we've been extended for the time being. So we need all of you who are interested in utilizing these data, who see value in utilizing these data, to do so. Please reach out to us. Let us know how you're using it, because demonstrating that value broadly across different application areas and for different types of partners is going to be critical. So showing up to support and demonstrating the value is really going to help us quite a bit in making sure we stay in operations.
Well, thanks so much, Christine. The next question is, what is the higher spatial resolution for the thermal bands on EcoStress?
We provide the products at 70-meter spatial resolution. I don't know if that was the question. if Glenn wants to unmute, he can say more about the ability to sharpen those further.
So we don't hear you at the moment. There we go.
Can you hear me now?
Yes, we can. Thank you so much.
Sure. Native resolution is actually 38 by 64 meters, which we then upsample to 70 by 70 meters, which is the data that you typically will get when using the data. But there are ways to sharpen the data down to finer resolution using VSWIR data. We do have that capability to get it down to the 10 to 20 meter resolution using Sentinel-2. I can put a link in the chat at some point this morning or today on some tutorials on how to do that if anyone's interested.
Perfect. Thank you, Glenn. Thanks for that response. So let's see here. Africa, did you want me to continue with some questions until for like 5 more minutes?
Maybe we can move to Dana's presentation.
Oh, okay, great. Yes, of course.
Thanks. And again, we will do our best to answer these questions afterwards, and you will receive the responses.
All right, are you guys seeing this?
Yes.
Excellent. All right, great. Well, thank you so much for having me here, and thank you, Christine, for kind of the introduction to mission applications and then also ECOSTRESS. I'm going to be talking about EMIT, which is also based on the space station. So they're just a really great kind of pair of instruments that are available for people to use at the moment. So I'm just going to start out so EMIT is an imaging spectrometer which collects data from the visible through the shortwave infrared. And so you're seeing that kind of radiance data, which is what the sensor sees at the top of the atmosphere. And then one of the products that I know we're going to be working with today, which is the estimated surface reflectance data on the bottom here. And so David, I know, is going to talk a lot about how we get from radiance to reflectance and what you can do with these types of data. But I'm just going to kind of give you a general overview about the fact that the surface of the Earth has a whole lot of different spectral signatures within this portion of the reflectance spectrum that allow you to discriminate between different minerals. If you're thinking about geology, different type of ecosystem properties, snow and ice characteristics, water characteristics, as well as information about the atmosphere through which the light has passed before returning to the sensor. So just to give you kind of a high level, the EMIT mission, EMIT stands for Earth Surface Mineral Dust Source Investigation. And so it was designed to really focus on kind of closing a gap in our understanding about the role that dust plays in the radiative forcing in the atmosphere. And the design to do this was focused on understanding surface properties where dust is emitted from, rather than attempting to catch very transient events of dust in the atmosphere itself. So you'll see the Spaceborne Imaging Spectroscopy all the way on the left here. And so that's where we're collecting the data for these dust emitting regions. What is the mineralogy of those areas? And then depending on the mineral composition, that those areas can have either a cooling or a heating effect in the atmosphere as that dust gets lofted. So by mapping out the dust emitting regions of the planet, we're able to parameterize Earth system models and try to understand the dynamics that play here. This is just kind of a cartoon image of how EMIT works. So it's a push broom sensor, which you can see on the bottom left here. It basically moves along with the space station and collects spectral data, which is at about 60 meters. And then we can take that data and use a variety of algorithms to generate mineralogy maps kind of across the surface of the Earth. And so, of course, this complements really nicely what Christine was talking about with the use of thermal data for for critical mineral exploration and kind of coordination together. So this is where we have EMIT coverage to date. I took this off of our Visions portal this morning, actually. So this is truly the most up-to-date look at all the data we've collected since launch. So you can see that, under the area where the ISS observes, we have a huge portion of the land areas covered to date, which has allowed us to kind of move past that original dust emitting region's focus and expand into a whole variety of applications that occur across a lot of different types of land surfaces. So I'm going to kind of highlight some of the application areas that we're interested in with the EMIT mission, and then I'm going to go into a kind of a deeper dive on a couple different examples, mostly highlighting things that are being done by our science and applications team, as well as other collaborators. So, we have products already that we're generating for mineral estimation at the surface. And so that kind of helps us understand critical minerals and surface geology. We can also generate information that helps us understand environmental hazards, including landslide, volcano risks, dust sources, oil spills, surface plastics, things to help us understand water quality in agriculture, also precision agriculture, food security. Think about wildfires, both kind of risk beforehand, burn severity, and then kind of recovery trajectories. And then last but certainly not least, thinking about water resources and snowpack monitoring as people, especially in the more drought-prone U.S. West, are trying to get a better handle on water resources as early warning detection. So the first thing this is a map on the top left here, which is very exciting. So this is a global map of minerals detected by the EMIT sensor. So this is really the first of this type of map that's been made across dust emitting regions. So it's very cool to see kind of the level of detail that we're getting here. And we can use this for a variety of purposes, including thinking about the location of different deposits that might contain critical minerals and rare earth elements, but also to think about the presence of acid-forming minerals and risks associated with acid mine drainage issues to help with environmental remediation and kind of responsible management of resources. So there's a variety of different applications for thinking about using these mineralogy maps. This is an example from Roger Clark, who's on our EMIT science team, who was looking at how we can start to use EMIT data to detect rare earth elements, which are much less frequently found on the surface of the Earth. So this is an example that he found, but this is something that we're hoping to kind of continue improving over time. And we have heard from a variety of folks that are using these data kind of in their pipelines for exploration activities. We also have a couple of Rose's team members, Dean Hively at the USGS and Jody Genowan at the USDA ARS, who are doing a lot of work looking at using EMIT and similar data for precision agriculture. And so they've been thinking a lot about understanding cover crop, functional group mapping, as well as kind of the quality of that cover crop residual, so that they can better understand kind of who is doing cover cropping, and then also understand how that's helping with nitrogen management, for example. So this is a nitrogen residue calculator that they've developed and they're using to help people make decisions about their cover cropping and nitrogen fertilizer application. And they're working currently to ingest EMIT data into this type of a tool so that they can, work with farmers to make better decisions that actually improves local water quality as well. We also have work that's being done both by Aisa Estrella, who's an EMIT team member at JPL, as well as Dan Souza, who's a Rose's team member at San Diego State. And they've both been kind of focusing on different versions of understanding agricultural plastic distributions globally. And this has been of great interest, especially as there's an increased interest in thinking about how plastic pollution kind of moves through ecosystems. And so agricultural plastics are often a source that result in microplastics entering both soils, waterways, and the oceans. And so starting to kind of get a spatial understanding and eventually temporal understanding of how that plastic is being used, where it's being used, what type of plastic it is, and how it's moving around can have an impact on kind of our understanding of that global plastic cycle. We're also able to think about how vegetation changes as you move from kind of healthy, green, well-hydrated vegetation into dry, much more flammable vegetation as we think about kind of understanding fire fuel distributions. What you can see here on the left is kind of an example of, in blue, like an early season, very happy, very green, grassy meadow, and moving into kind of a fully senesced version of that exact same meadow in red. And as these changes take place, you can see that there's a lot of nonlinear changes that occur throughout this spectrum. And this can give us some information about different characteristics of vegetation that suggest flammability and could be potentially used for better fire management. We did also want to highlight that we have started to also be able to acquire active fires at night. So this is something that we've been doing in coordination with the NASA Fire Sense team. This is kind of related to some of the things that Christine was also talking about fires here. I think this is actually the same group at San Diego State, and they've been working with both ECOSTRESS and EMIT data, as well as a variety of airborne sensors, to think about understanding burn severity in different places, thinking about recovery, think about prescribed burns. And so there's a lot of kind of ongoing and exciting work in this area that I think we're all looking forward to kind of seeing more results from. There was recently more work done by that same group, as well as Christine Lee, who was just speaking, to think about the impacts of wastewater being released into the Pacific Ocean at the border between San Diego and Tijuana. The Tijuana River is depositing a large amount of wastewater in that region, and so they've been able to use EMIT data to detect kind of those plumes and help discuss with a variety of folks, including the EPA and the County of San Diego, how they might manage beach closures and give them a sense of kind of where some of those plumes are moving. So this can be really useful for kind of public health and safety. And then finally, this is a project that EMIT team member Kelly Lewis has been working on, which is looking at using EMIT to think about algal pigments and organic matter and sediment plumes in these areas. In this case, she's looking at a variety of ponds that are used as catfish aquaculture. And so thinking about how we can use these EMIT overpasses to understand phytoplankton dynamics over time and evaluate and guide management practices for these areas. So with that, I just mostly wanted to give you a variety of examples because I know that David Thompson is going to go into a deep dive on a variety of kind of the early processing stages of data, and you'll get to play with them yourselves. But just to kind of whet your appetite for the types of things that you can potentially do using these data sets, and especially when they're in conjunction with a variety of the ECOSTRESS products. So thank you so much for the time. And if you'd like to join our mailing list or Slack workspace, please be in touch with me. My email's here, and I'm sure it's posted somewhere on the agenda. So thank you very much.
All right. Thanks so much, Dana. At this point, we're going to transition directly to our next speaker, Morgane McGibbon, who is going to provide a PACE mission overview and discuss applications for PACE data. And with that, after this next session, we will continue forward with a question and answer 15-minute break. All right. So thanks, everybody. Thanks, Morgane.
All right, everybody. Yeah, thank you, Jennifer. My name is Morgane McGibbon. I'm the PACE Mission Applications Lead out at NASA Goddard Space Flight Center. And today I'm going to introduce you to NASA's new hyperspectral mission PACE, I'll give you an overview of the mission as well as a high-level overview of our applications. Basically, yeah, here's the outline. I just said it basically. We're going to talk about why PACE is important, talk about our applications, and also I have a couple slides on resources that are going to help you get to work with PACE data. So jumping into the mission overview, if there's nothing else that you get from today's talk, I hope you learned this slide. Why PACE? Why do we care about PACE? So PACE was just launched in 2024, and it's the only satellite platform that provides near daily global hyperspectral satellite observations of Earth. It has a unique combined technology and coverage in the field of observation that is providing a lot of new information about our Earth. In particular, we have that hyperspectral sensor, which sees over a really broad, kind of uniquely broad range of wavelengths globally, as well as 2 polarimeters that look at our atmosphere and get us some high accuracy measurements. PACE Earth observations also are multidisciplinary. So that means we're learning new things about phytoplankton in the sea, plants on the land, particles in the air. And we anticipate PACE is going to be fueling a lot of new breakthroughs and give us new practical tools to help support society with Earth observation data. To give you a little bit of context, if we zoom out thinking about the NASA Earth fleet, this is a really neat QR code if you want to go check it out. It shows live where all these satellites are, basically to give you a perspective of where PACE sits in this context. So this diagram basically starts with Terra and Aqua here in the middle, spiraling out in time. So these are older missions going out to newer missions. This stripe here, we have EMIT, and over here we have PACE. So where EMIT is aboard the ISS and gets us very high, kind of high spatial resolution, I guess approximately weekly hyperspectral information from the ISS. PACE is a new observatory that gets us hyperspectral resolution data at a bit broader resolution, more like 1.2 kilometers every 1 to 2 days. As a quick overview, we were launched specifically in February of 2024. We released our first data in April of 2024. We have the 2 instruments that I already mentioned. We have OCI, which is our hyperspectral scanning radiometer, as well as HARP-2 and SPEX-1, which are multi-angular polarimeters. PACE is a global polar orbiting satellite with a 1,300 local equatorial crossover time. It's a 3-year mission with 10 years of propellant. And of course, our data products are free to everyone. Our goals are to advance and extend ocean biological, ecological, and biogeochemical data records, as well as cloud, aerosol, and terrestrial data records. Let's talk a little bit more about each instrument. We have the Ocean Color instrument. This is the first one and really the only one required by the mission. This is a hyperspectral scanning radiometer that gives us spectral resolution from the UV, from the ultraviolet through the visible, through the near infrared at 5 nanometer bandwidth and 2.5 nanometer steps. We also have 7 shortwave infrared bands. The time coverage is 1 to 2 day global, which is great for hyperspectral information. Our spatial resolution is 1.2 kilometers at nadir, and that lower spatial resolution allows us to have the higher temporal resolution. We also have these 2 polarimeters, which we won't really be covering today, but just so you know, they're here. We have a hyperangular polarimeter called HARP-2, and also a hyperspectral polarimeter that we call SPEX-1. And HARP-2 has a footprint similar to OCI's, and SPEX-1 has a very kind of narrow swath. If you want more information or you want to see what this looks like, this is a great animation. This QR code shows you how these instruments cover our Earth. And really the qualities of each of these instruments are novel and advanced and unique in their own right. And altogether they do represent, they're stronger together as most things are, and they represent the most advanced global ocean color and aerosol mission to date. As I mentioned, we're going to today's talk from here on is really going to be talking about OCI. That's our hyperspectral instrument and the products from OCI. So as I've already said, the PACE observations span our entire Earth's system. We get data products on our aquatic, atmospheric, and terrestrial domains. And also, we do provide advanced products, of course, that are only from PACE OCI that are allowed by the hyperspectral resolution. We also serve several heritage products that you all might be familiar with using, depending on what your background is, from MODIS and VSWIRs and other Earth observation satellites. If you want to see a comprehensive list, this is our PACE data product table. This is a live document. Bookmark it if you're interested in PACE. It tells you every data product the mission serves now and plans to serve in the future for all three instruments. And so, why are we excited about PACE? PACE at its core is an ocean and atmosphere mission. And for decades, we've seen invisible or microscopic stuff from space, right? With MODIS, VSWIRs, other platforms. We've looked at things like phytoplankton, which are microscopic algae. These are images of what phytoplankton, look like. They're tiny, but we can see them from space. Same thing with aerosols. We're looking at aerosols with PACE data, which are particles in our atmosphere. And, for decades, we've had this kind of information, which has revolutionized our understanding of Earth. This is the total amount of phytoplankton distribution across the Earth, as measured. This one's actually measured by PACE using the chlorophyll pigment. So this is phenomenal. PACE is now taking a step further, advancing this even more by moving into, for the first time, being able to see globally different phytoplankton types from space. Why do we care about phytoplankton types? Why isn't total phytoplankton that we've had all this time enough? The type of phytoplankton present tells us something really important about how much carbon is exported from that area, how much food is available in that area. Keep in mind, these are photosynthesizers, so they take up carbon dioxide, they release oxygen, up to half of the air we breathe, and they also feed a very hungry ocean, as well as you if you eat seafood. So knowing which phytoplankton are out there is super important. It helps us better understand our oceans and also better support things like fisheries and, advance Earth observations from space. And I know a lot of folks, perhaps the majority of folks here, are actually land folks. PACE has land data as well that is just as phenomenal as our ocean data. This image here is a first. It's also combining 3 different data products, which I should have mentioned on the previous slide. I didn't actually, maybe I'll detail this one a little bit. I didn't actually detail what each of these things are. Sorry about that. This is 3 different phytoplankton types. So we have 2 kinds of cyanobacteria, which are Synechococcus and Prochlorococcus, and in pink and blue. And then we have picoeukaryotes in green. So these are 3 different phytoplankton 3 different phytoplankton measures put together into one visualization to give you an overview of how phytoplankton groups are changing in the Atlantic over time. This is extremely exciting and something that PACE was made to do, and it helps us understand our Earth better. Similarly, on land, plants on land have pigments as well, just like the algae in the sea and other kinds of optical fingerprints that help us observe them from space. This is another first from PACE. This is our first year of global seasonal change in 3 different plant pigments happening at once. So similar to phytoplankton, where we looked at chlorophyll that we've looked at for decades from space, we've also looked at terrestrial vegetation from space for decades using metrics like NDVI, the Normalized Difference Vegetation Index, which kind of looks at the brightness, estimates, chlorophyll content based on, or amount of vegetation based on plant brightness. Here, this is completely different. We're looking at, the green pigment chlorophyll A. We're looking at the blue pigment, or in blue, we're looking at anthocyanins, and in red colors, we're seeing relative amounts of anthocyanins in red and carotenoids in blue. And this is showing how they dynamically change over time. With NDVI, you don't see this level of detail. When you have this much information about photophysiology of plants, their pigment distribution, their pigment content, you have more information about what type of vegetation you're looking at, similar to how we're looking at phytoplankton type in the previous slide, as well as health status, productivity, and leaf area. So what are we doing with all of this fantastic data? That's, of course, we are pushing, this data is being put towards foundational research, of course, advancing our understanding of the Earth system from space. And it's also going towards applied research, such as, how can we use this PACE data for societal benefit for things like, food security, fisheries, water quality, disasters. PACE is, of course, able to support applications across all of these domains with its cross-disciplinary data products. And if you don't know what applications are, it basically means innovative uses of NASA's PACE data to help improve, kind of on the ground activities, decision making, maybe support businesses by giving them water quality information. There's a huge number of ways that PACE data are used on the ground to provide practical solutions to meet societal needs. And the applied research is what basically scales and integrates these fantastic PACE data products and the foundational science behind them into user policy, business, management activities, or whatever else our end users may need. Our end users may be individuals and groups, public and private sectors. They could be national, international, local, and global scales. PACE has a very wide reach with its applications, kind of similar to what you saw with EMIT in this kind of cross-disciplinary coverage. The PACE Applications Program has the overarching goal of accelerating and supporting translation of PACE's advanced data into societal action across many domains. We build new partnerships between the PACE data producers and, any kind of end users, as well as other missions and across sectors. We ensure accessibility, usability, and actionability of PACE data. And also we foster and quantify the societal value and broad utility of PACE across the world. And we do this in several ways. For one, we have some events, which I'll give you a link to later, to engage our communities. And we have a couple of different communities. One of them you all are welcome to join. This is our community of practice. This is basically anybody who's interested in using PACE data and staying up to date with our mission. I invite you to join our community email list by scanning that QR code there and following the directions. This will keep you up to date on all PACE mission news, PACE applications news, and all of our events that are coming up in the future. We also have a science and applications team, which is a competed science group. And these are NASA-funded scientists that work on algorithm development, as well as applications and validation of data. And we also work with, we have an early adopters program as well, similar to what you've heard about from EMIT. And we call them applications partners post-launch. Before launch, everybody is an early adopter. And these are basically researchers that have applied projects and needs, and they're teamed up with stakeholders on their end. They're united, or they're connected with their end users, and they connect with us to help advance their work. The applications partner, this is an example of a few of the folks that we have. We don't have time to go over all the projects. Unfortunately, there's lots of great ones. Please check out this website to see what our early adopters have been up to. And you'll see that we work with individuals and groups across public, private, nonprofit, university, and all sectors. Just whoever is looking to integrate PACE data into their decision-making, resource management, or other practices. Our partnerships, like I mentioned, specifically amplify research and development efforts and accelerate the translation of PACE observations into action. If any of this sounds familiar, sounds like it could help your project, take a look at our webpage and consider joining us. We review applications for this program about quarterly, and we welcome new folks to join us. Feel free to reach out to me if you have any questions about that. And, kind of like Christine was saying, this is one of several examples of how we can show the value of PACE, which is really important to our Earth missions. These are the stories of how our data is benefiting society. So I hope you'll consider joining with your project. Now let's talk about some actual, let's talk about some examples. What is PACE doing out there? How are we applying PACE data? So we have all new, hyperspectral data products like the phytoplankton community composition products you just saw. We also have spectral optical water properties and data that covers our coasts, our oceans, and our large inland waters. And with this information, we're advancing water quality management and helping to better understand aquatic ecosystems, which can help us identify and track harmful algal blooms, Those are the blooms that can make your seafood or your drinking water toxic or cause folks to cough at the beach. We can better identify and track them with PACE data. We can also better assess the health of fisheries and aquaculture, evaluate and maintain ecosystem health, identify things like oil spills better or floating matter like sargassum, the large macroalgae that hit the Gulf Coast. Also, post-disaster water quality impacts, especially those that kind of cause inundation in the water and large changes in the optical properties of the water. These are examples from a couple of our early adopter projects. This one up here, they're looking at how to better detect harmful algal blooms in the southern Benguela and using PACE's advanced data. And similarly, we have a National Oceans and Coastal Information Management System aquaculture decision support tool that is also looking to incorporate phytoplankton community composition from PACE to better help fisheries make decisions about the locations they fish in. Here's another example. So one of our PACE early adopters, Bingqing Liu, she's at the University of Louisiana Lafayette. She is not only an early adopter, but she became recently this year a science and applications team member. And their work is looking at improving water quality for aquaculture health and suitability in the Mississippi Atchafalaya River system. So what they're looking at, they're down here in the tip of Louisiana in the Gulf of the United States. And here there's a lot of aquaculture, and they experience unexplained die-offs that are accompanied by cyanobacterial algae blooms. And with PACE's advanced spectral detail, they're using field data, PACE and actually EMIT data, and machine learning to identify the spectral signatures unique to the different phytoplankton types. Here you can see this pink one is separating the cyanobacterial bloom from other blooms. So it takes this total chlorophyll or this total estimate of all the phytoplankton in the water, and here they are extracting the cyanobacteria bloom in exactly that area, working towards having information for these aquaculture farmers to help them understand what the environmental conditions are around their operation. This helps them better respond to risk in case of any kind of harmful algal bloom detection. Moving from the water to the land, we have PACE applications. There's we provide all new information on vegetation, land use, land change, and more, kind of like that the visualization you saw earlier. And these provide great insight into the dynamics of terrestrial vegetation, biochemical and functional characteristics. And we anticipate this is going to help advance monitoring of wetland ecosystem health, forest health, land use, land change, and also, kind of broad scale, maybe regional scale agricultural practices and terrestrial ecosystem diversity. If you're familiar with NDVI, which I mentioned earlier, the Normalized Difference Vegetation Index, these products that we have now very much amplify, or they have a similar ability to tell us a lot of information as NDVI did, but we're getting more information right on the pigment content of the plants. And this is providing us new ways to look at vegetation health and productivity. Here's one example. So we've looked at productivity from space using NDVI for some time, but using the spectral reflectance data alone, so just the spectral reflectance data from PACE, one of our science and applications team members has developed an all-new PACE gross primary productivity product. It's an independent measurement, unlike previous satellite GPP models such as those developed with NDVI data. And as we know, independent measurements are more robust than ones that rely on, layers of other kinds of data or other sets of uncertainty. And it's only PACE, the unique combination of PACE's hyperspectral capabilities, its near daily coverage of the regions of interest, and that give us the ability to do this. And this supports agriculture and forestry applications, this GPP product, by independently describing seasonal and transient variability in productivity in a kind of new and more robust way. So we look forward to seeing where this goes in realms like agricultural, ag monitoring, etc. So how about PACE applications in the atmosphere? Again, we have atmospheric data products that are advanced. They help us support air quality and its implications on human health, as well as support weather and climate applications. For example, we have an early adopter, Loria Salazar et al. Out in Oklahoma. They're looking at how to inform regional health alert forecasts related to pollen, dust, and smoke using PACE data in tandem with ground data, which is what's shown here. This is the Oklahoma Mesonet, which is a huge network of meteorological stations on the ground. We also have folks investigating the influence of aerosols on aerosol and cloud interactions. And also, PACE data can give proxy air quality information in locations that lack ground station infrastructure, among other applications that we're pretty excited about. This is some more great data that is enabled only by PACE. This is from Zach Fashnot et al. In our science and applications team as well. They have developed an all-new high-resolution nitrogen dioxide data product. So while nitrogen dioxide itself is not a new measurement from space, the ability to see it at this spatial resolution, the 1.2 kilometer resolution of PACE, is novel. So here we have PACE data over the LA area on 3 different days, a Sunday, a Monday, and a Tuesday. You can see the big difference between, kind of rush hour traffic and how it impacts the nitrogen dioxide content in the air. And you can also see with PACE that we can see basically down to the highway level. Whereas with TROPOMI and TEMPO, which are NASA satellites that look at trace gases like nitrogen dioxide, they have a much coarser resolution. And this is actually complementary. So if you think, tempo data, these are sub-daily, I think hourly types of information on which ways plumes move. So if you have this high spatial resolution information from PACE, you can look more clearly at emission source, and then you can use along with that tempo data to see which way plumes are going over time. So this is a really exciting data product that we look forward to be providing soon. We aren't providing it yet, but it is in the pipeline and it is getting there, along with ozone. O3 as well also is anticipated to be provided by this group as well. This also has applications to farming. Nitrogen dioxide information from space is utilized for different farming models, and we hope to see growth in applications areas there as well. So here in the last part of the talk, I want to talk to you about PACE data resources. So I just have a couple of slides. So this would be a talk in and of itself on where to get data and how to use it. In the interest of time, I'm going to point you to resources where you can do just that on the next 2 slides. First of all, if you're interested in accessing PACE data, we have made a website that's supposed to be a central location for all the kinds of information you need to work with PACE data, such as which version is the PACE data. Our PACE versions change every several months as the data are matured. Which version are you working with? How do you access PACE data? What kind of resources are there? All these answers are on this webpage, so please take a look at it. Also, if you want to access PACE data, there's kind of 3 places that you want to go. They are listed on this page, but I'm going to talk about each one a little bit right now. NASA Worldview is a really great tool for visualization. So you're not going to get data numbers from this one, but it's a really great, kind of point and click way to look at what coverage in your area looks like, for example, with the PACE data. Right now, we only provide chlorophyll A, true color reflectance, and photosynthetically available radiation, which is a water product. Sorry about that. And we do have more products to come on Worldview, but right now it's just those 3. But you can look at it to kind of see what coverage looks like and look over time, make images and videos pretty easily. NASA Earthdata is, of course, your go-to for downloading our data. That's served on the Amazon cloud. There we have provisional data from all of our instruments, OCI, as well as the 2 polarimeters. We have a whole host of data available. You can also access data through the NASA OBDAC. In general, this is kind of an area that folks use to get test data that is not yet released to Earthdata if people are wanting to kind of work with earlier versions of the data, or they can also get kind of global level 3 4-kilometer products there as well. But your go-to source generally is going to be NASA Earthdata, and you'll hear more about accessing data in general from Earthdata today. This last slide is just a lot of text. It's a lot of links, but I really want you all to have a copy of this in the slide deck so you'll know where to go to get started working with PACE data. As I already mentioned, we have the PACE data access page, which is the one I just mentioned on the last page. Start there, bookmark it. We have our data product table. I've already mentioned that one as well. Make sure that you check it out to see what kind of products we are offering. We have a help hub. This is where our DAC is compiling lots of different kinds of information on PACE and tutorials for PACE as well as other missions. There's Jupyter notebooks, there's access to training tutorials and all sorts of information there to help you get started. We have events listed on our events page. These are events that we hold, most of them virtual events in support of our community of practice and other communities in order to help folks work with and apply data and share findings of what's happening with PACE data. Again, I encourage you to join our community of practice. That's our email. Join our early adopters program. And also we have an events archive if you want to see recordings of events that we have held in the past on many of PACE's data products that I actually gave examples of today. And with that, I will take any questions that anybody has.
Can you highlight how ECOSTRESS data can be used for critical minerals, geothermal, and coastal mapping applications? Really interested in using this data. Maybe just keep it at a high level. Certainly, our speakers can follow up with all of these webinar participants offline as well, because some questions may require additional, a more in-depth response. All right. Did you hear my question? Can you all hear me?
Yes, I can hear you. I don't know, Christine, Glenn.
Christine, or can you highlight how the ECOSTRESS data can be used for critical minerals, geothermal, and coastal mapping? Let's see. Applications. Really interested in using this data, and I'm trying to see if there was a response earlier to that. Anybody? If not, why don't we go ahead and move? Oh, go ahead.
Can you just repeat it again quickly, Jennifer? How can it be used for critical?
Of course. So the question is, can you please highlight how the ECOSTRESS data can be used for critical minerals, geothermal, and coastal mapping applications? I'm really interested in using this data.
Okay, that's a lot to cover. That's 3 pretty broad topics there. Is there a way to do this offline, or I could go on about each of those for quite a while.
All right, let's hop on to the next one. Since I've got you on the line, is ECOSTRESS data available for the ocean depth?
No, it's a surface mapping mission, so we're only sensitive to the top few micrometers of the surface.
Okay.
Since it's thermal infrared.
And as a follow-on to that question, we had a different webinar participant ask, I would like to know to what depth the hyperspectral data can reach. We may need more details for that question.
What depth and was it in aquatics? Was that the question?
So this is a question that took place during the ECOSTRESS and the EMIT presentation. So maybe if this particular user could add some additional details, that would be helpful.
Yeah, and maybe I'll note that, for some of the questions that I've seen here includes some that haven't been answered yet. I think both Glenn and David are going to cover, some more of the details and kind of get into the nuances of using those data. So,
That sounds good.
May be useful to kind of ask after that stage once there's a context.
Sure. All right. So why don't we hop down to the Q&A? Let's see here. I do see. I'm trying to cover those that have not been responded to the text response. So again, trying to go in order, but there are a number of questions. So let's see here. Okay, we covered that. Do you see a possible scenario where ECOSTRESS data could be used to develop subsurface water utilization models that parameterize ET and photosynthesis chemistry to optimize surface vegetation volume?
This might require a separate conversation as well.
No problem.
Thank you for the question, though. That is very interesting.
Okay.
Jennifer, I highlighted one for prioritization for the EMIT data, and this may be one that later there will be more information, but since we also have Dana here, I can read it if it's okay.
Sure.
Yeah. Which atmospheric windows are being used for mineral mapping based on EMIT data? Don't you remove part of the electromagnetic spectrum at 900, 1,000 nanometers, and 1,100 and 1,200 nanometers?
Yeah, thank you, Africa. Yeah, I did answer that one in the Q&A, but it's a good question. That in one of the slides I showed the full spectrum of some of the mineralogies which are collected in situ, so without the issues related to the atmospheric water vapor bands. And so for the actual EMIT modeling of the minerals, that yes, those bands are removed as part of that. So apologies for the confusion there, and I will update those slides so that the atmospheric band components are removed, even though we have those data for the surface. We're obviously not using them when we have to be looking at something through the atmosphere.
Okay, thank you, Dana. The next question is, can ECOSTRESS-based WU or WUE, so I guess that's the water use efficiency, be validated against lysimeter or field-based measurements?
That is also a really... Oh, go ahead.
Okay.
I was probably going to say a similar thing to you, Christine. That's a very, very difficult thing to do. We have validated the ET product, which is a component of the water use efficiency. But to validate water use efficiency, you'd need to validate the gross primary production as well. And to do that, I believe you need different types of light use efficiency models in addition to in situ data. So it's a very difficult problem, but I think it is possible.
Okay, well, thank you very much for that, Glenn, and also Dana. So the next question is for Morgane. Are the pigment maps derived from radiative transfer models? And then as a follow-up, can the pigment maps be accessed publicly?
I'm assuming you're talking about the water ones. I don't know the exact model behind how they are devising the phytoplankton community types. I can link you to the paper in the chat and the algorithm information. And so I don't know how to specifically answer that question, whether we're using radiative transfer models or not, or to what extent they're being used. But you could figure that you can find out from taking a look at the papers that detail the indexes. If you were talking about radiative transfers through the atmosphere and the terrestrial, I don't know if that applied to the terrestrial, but all of these products I showed today, both those products that show the phytoplankton community types as well as the terrestrial vegetation indexes, yes, those are all available right now on Earthdata. And what was the second question?
Well, you basically just answered it. Are they available on?
Oh, okay, yeah.
Yeah. Okay, and so the next question again for you, Morgane. Could you please provide further information on the techniques or methods used by PACE data to detect the biosignatures?
I can give high level, information. That the takeaway is that each of the algorithms that we provide right now and in the future that differentiate biooptical signals, they all kind of have their own approach. So the terrestrial vegetation index that you saw in my talk uses something very much like the normalized difference water vegetation product or difference product. Those products are all kind of ratios of different bands. So it's not using the full hyperspectral signal, but it is using parts of the signal that weren't available from previous missions to do basically band ratio math to get those vegetation indexes. Or there was the one that I also showed in the talk where they were looking at cyanobacteria specifically in a specific area off the coast of Louisiana, and they were using a mixture of field data, machine learning data, and also PACE. And I do believe they might be using EMIT data on their project as well to put all that information together to try to identify what the spectral signals of interest are. So in that case, they are using the entire hyperspectral signature. There are many examples, and they very much vary by question, right? Are you looking at regional information? Like Moana is looking, that's the algorithm that we showed with all the different phytoplankton types. That is looking at the Atlantic Ocean specifically and very broadly. And it has one kind of approach. And then, we also have algorithms for looking regionally at more specific questions of like a certain harmful algal bloom type. So you can imagine there's a very broad number of examples, and I listed just a few of them. So I hope that helps answer the question.
Yes, thanks, Morgane. So the next question is, when is the level 2, level 3 HARP2 data expected to be released? Furthermore,
go ahead.
Sorry. Nope. Furthermore, what is the expected format of the aerosol size distribution product?
Oh, goodness. So those are, I don't know the answers to those off the top of my head. We do have, I don't know if Sky, we also have another person on our team in the chat. I don't know if she knows the answer to that. I can look it up for you and make sure that the answer is in the question and answer document that will be distributed with this webinar. But I think I know the answer to the first one, but I'm going to just wait and give you the exact answers after the webinar to make sure I get
Okay. Okay, that sounds fine. The next question is an EMIT question. How does the performance of EMIT data compare to VSWIRs in terms of spatial resolution and sensitivity when it comes to detecting active fires, especially small or low temperature events?
I will have to defer to David on this one. I don't know enough about the exact specs of VSWIR's fire detections to be able to comment on that. But David, if you have some initial thoughts, or else we could also get back to them on this question.
Yeah, I think we should probably get back to you on this. VSWIRS has a day-night band, which makes it a little bit different from EMIT, which does shortwave spectroscopy. So they're really very different measurements. But if you have a specific application in mind, we'd be happy to discuss with you offline.
Something that I can do on my end is provide some information about our fire information for resource management system, which provides access to both VSWIRs as well as MODIS and some Landsat active fire and thermal anomaly data sets, if that would be helpful. Let's see.
Jennifer, may I just add that? Just expand on David's response of VSWIRs and the spectral bands that are being used for the data product in VSWIRs and MODIS are different of what EMIT is collecting in the visible to shortwave infrared. And those resources will be great to make that differentiation. Thanks.
Thank you very much, Africa. I'm trying to scan back up through the Q&A, and then I can hop back up to the chat, and then we probably have, let's see, the next talk is David, and we've got just 4 minutes. Many of these questions require additional feedback offline. All right, so let me hop back up to the chat really quickly. And if you could enter any questions you have in the chat into the Q&A panel, that would be super helpful. Really appreciate that a lot. Okay. Bear with me for a moment here. Take a look at the Q&A panel. Okay. I would like Okay. This is a further, I think many of these have been addressed.
Jennifer, there is one from Mayowa Latif in the chat that I don't think has been answered.
Okay. In the chat or the Q&A?
Sorry, the Q&A. My bad.
Okay.
It was asked earlier, but then they were able to resend it, so it shows up a little bit.
Okay, good. Let me go look. Yes, I had asked for, bear with me as I...
And this is a fairly detailed question, so again, you may be better off waiting to see Glenn's presentation and then asking if you still have questions at the end of that.
Yes, I see it. And I'm sorry that I missed it earlier. Again, it's when the questions are coming in so quickly, we do try to acknowledge them as quickly as possible. So I'll read this aloud, but again, we may need to address it later on. I am encountering significant challenges when using ECOSTRESS radiance data, as each acquisition exhibits a spatial shift or misalignment in its swath, making consistent time series analysis difficult. Furthermore, while I can mask the substantial cloud contamination, I am seeking guidance on methods for co-registering these swaths across acquisitions and whether atmospherically corrected ECOSTRESS radiance data or a recommended atmospheric correction workflow workflow, excuse me. So I don't know if there's any input that can be provided here.
Yeah, I mean, I can broadly answer some of that. In my presentation, I will speak about some atmospheric correction techniques, which I'll get into more detail with. In terms of the spatial shifts and geolocation, that is definitely a quirk that we have with ECOSTRESS, and a lot of it depends on the amount of cloud that we have on any given orbit, which affects our geolocation accuracy. We are actually working on a GUI this summer, which will be able to correct the geolocation for any image on the fly, which is a really neat tool that one of our students here are working on at JPL this summer. So we're hoping that, that'll be made available at some point in the near future on GitHub, some publicly available space. There are flags that we do have with the data that tell the user whether any given scene has been geolocated, if it's the best quality geolocation, if it's poor geolocation. So there are some general qualitative flags that we have, but in general, the geolocation can vary from orbit to orbit depending on cloud.
Well, I really appreciate that response, Glenn. And so with that, I think it's time to transition to our next speaker, Dr. David Thompson, and he's going to provide an introduction to visible shortwave infrared imaging spectroscopy. So with that, David, let me toss you the presenter role. And you have the presenter role, so wonderful.
I will just share my screen here. And hopefully you can see my slide presentation now.
Yes, I am starting to see your slides.
Perfect.
Yes, I do.
All right. Well, thank you, everybody, for joining. I'm really excited to see this vigorous discussion already. I'm going to take a few moments to dive a little bit deeper into some of the technical aspects of shortwave infrared imaging spectroscopy or hyperspectral imagery, using EMIT as an example. So you've already heard from Dana a little bit about the EMIT mission. We're going to go a little bit deeper into how the data processing works, give you an idea for the measurement technique, and also how spectral fitting can be used to estimate geophysical parameters from imaging spectroscopy data. And I'll close with a few words about the future of imaging spectroscopy with NASA. So here on the agenda that I just described verbally is an example representation of an imaging spectrometer data cube. So if you wonder what we've been talking about, as far as what the data products actually look like, it's a 3D array where for every point in an image, we get a full spectrum of information. Now, most of you know this already, so apologies if it sounds a bit pedantic, but it's worth revisiting just to talk about the richness of this data product and how much information is present in every one of these scenes. It's really remarkable, and especially with the advent of instruments like EMIT and a future global VSWIR mission like SBG, it really unlocks new ways of viewing the Earth that go far beyond what we've been able to do in the past, really being far more quantitative and precise about our remote measurements using analytical laboratory techniques essentially and applying them in open air to measure properties of the Earth system. So this is a really exciting measurement, and EMIT is now allowing us to apply it on really global scales for the first time across the VSWIR range. So again, the agenda, I'm going to talk about the measurement process, walk you through what that looks like for the case of the EMIT mission, and then go into a little bit deeper dive on algorithms, in particular how we estimate or how we invert physical models to fit spectra. And I'll talk specifically about atmospheric correction, which is a really important operation that many people have asked about already, to give us an idea of how that works in the case of imaging spectroscopy. And it's a good thing to know, even if you are already using processed reflectance data that you've downloaded from the NASA archive, knowing how we got to that reflectance is going to be really important to interpret those data properly. So we'll spend some time on that, and then a couple more words about SBG. Okay, so these are the photons that we're working with. This plot shows all of the energy that's available for passive remote sensing of Earth, at least in the visible through thermal infrared range. And it comes from two major sources. There's the solar reflected energy that you see in this red curve here. That's the solar illumination onto the surface. The sun is a very hot black body, and so it puts out a lot of energy in the short wavelengths from the UV out through maybe 2.5 microns or so and tapers off after that. And then Glenn afterwards is going to talk about how we interpret these thermally emitted photons from the Earth itself glowing at more or less room temperature. And then behind you see overprinted the atmospheric transmittance. So a gray area is absorbed, and then white area shows where photons are able to make it down through the atmosphere, reach the surface, and then come back to the sensor so that we can interpret them in order to understand properties of the Earth system. So I said the word VSWIR for visible shortwave infrared imaging spectrometer, which really covers this range from the UV to 2.5 microns, 2,500 nanometers, capturing the majority of solar reflected photons. And they're really just a huge number of different processes to which these photons are sensitive in the Earth's atmosphere and on the surface, which makes it a really flexible instrument for doing a lot of different remote sensing applications. This is how one of these sensors works. So I mentioned before it's a data cube, a three-dimensional object, but all of our detector arrays, like the ones in your phone or any camera, are two-dimensional. So we have to figure out a way to build up that third dimension. And this cartoon describes that in detail. So in a push broom configuration, like most modern VSWIR imaging spectrometers, you have a linear field of view on the ground. And the light from this linear field of view enters a telescope, is imaged onto a slit, and then dispersed by some dispersive element in a spectrometer and cast onto this two-dimensional detector array. So we have one spatial dimension, and then the rainbow represents the spectral dimension. So we sort all of those photons by wavelength and turn that into linear distance along that focal plane array, and can use that to record all the different spectral channels that we like at every location in this cross-track field of view. And then to build up our third dimension, of course, we push that field of view along the surface of the Earth by flying an airplane or orbiting a spacecraft at 7 kilometers a second, sweeping out this cube. And I've showed here what a single spectrum looks like. So here you see a zoom in on that red solar reflected range from the previous slide, showing these water absorption features that were mentioned before, other absorption features due to gases in the atmosphere like carbon dioxide or methane, and then a much subtler undulation of this radiance spectrum that it comes from the properties of the surface, objects on the surface preferentially absorbing and reflecting radiation based on their own chemical composition. The molecules vibrate at different frequencies and preferentially absorb certain wavelengths and impart these very distinctive signatures that let us figure out what the surface is made of. So all of this is present in this one spectrum. Okay, so the components of a radiant signal, like I mentioned before, contains a lot due to the atmosphere and then a part due to the surface as well. Dana showed a version of this diagram before, but I want to revisit it a couple times during my talk because it's really important to grok this fundamental difference. So the radiant spectrum represents illumination that we receive at the sensor, and that has imprinted on it all of the different processes of scattering and absorption from these solar photons that transit from the sun to the ground, or just simply scatter off particles in the atmosphere and then get back into the sensor. So you see in the radiance all of these gas absorption features, for example. There are other subtler effects due to particle scattering and things like that. But there's a fraction of these photons that reach the ground and come back to the sensor. And so what we really care about in doing remote sensing of Earth's surface is not the radiance at the spectrum, but it's a property of the surface that's independent of what atmospheric conditions happen to be at the time of the overflight. And here, this is the reflectance spectrum. You can think of if you were standing at the surface with the light source and a sensor shining light onto that surface and then measuring the reflected photons, you'd get something like this. This is the ratio of incoming or outgoing to incoming radiation. And I'll give you 5 seconds to pause and look at this reflectance spectrum and see if you can guess what it's of. And as a hint, these are the visible wavelengths on the left side. So we have blue, green, and red here. Well, if you guessed vegetation, you're right. This is a green peak that you see caused by chlorophyll absorption in the red part of the spectrum. And so this is a chlorophyll absorption feature, but we see this green part is a little higher. So our eyes believe this is a green object, but there's a lot more going on in the shortwave infrared. Lignocellulose features out in the shortwave. In the near infrared, we have liquid features due to water absorption in the plant tissues. So there's really a lot more happening. And with a VSWIR spectrometer, we can really fit physics-based models to all of these different components to fully explain them once we have this reflectance spectrum in hand. So it's really, generally speaking, a two-part analysis in which we first try it and infer the reflectance and then analyze these reflectance data to understand what the surface material is made of, what properties, physical and chemical, it has. So this is the data analysis. This is for the EMIT mission as one example, but most imaging spectrometer analyses of Earth's surface have the same general workflow. So you start by calibrating the data, the sensor. That means ascribing these horizontal and vertical axes to it. So radiance, illumination, energy per unit time arriving at the sensor, and then the wavelength scale on the horizontal. So we have a wavelength assignment and response for every channel. That's very important. Then we estimate the surface reflectance portion of that signal. Then we analyze the surface reflectance spectrum. As Dana said, with the EMIT mission, we really care about mineralogy. So we fit different mineral library spectra to come up with mineral maps and then aggregated that into Earth system model scale products for ingestion into Earth system models. But there are a lot of other things you can do that I'll describe in a second with this level 2A surface reflectance. Here's one example of a surface product that's used for a lot of science applications. It says non-photosynthetic vegetation. This map shows both non-photosynthetic vegetation in red, but also photosynthesizing vegetation in green. The non-photosynthetic stuff is like woody stems and plant tissues, and it has a very distinctive character with lignocellulose features out at in the 2 to 2.5 micron range. And so in this example, you can see as we increase the fraction of non-photosynthetic vegetation in a spectrum, we see it go from black to red, and you see these features start to appear. So we can fit physical models that are very quantitative about the fraction of the signal that's coming from these woody stems and plant tissues and other, like what is essentially fire fuel load. You can also use it to look at fallow fields and tillage and other agricultural questions too. So this is a really useful product that we're now on the EMIT mission beginning to generate at continental scales. Here are more examples of mineralogy showing how we fit mineral signatures in reflectance spectra. Mineral compounds have their own specific vibrations that give very distinctive and clear fingerprints of their presence on these reflectance spectra. You can see calcite and carbonates have distinctive absorption features. The kaolinite green one down here in the lower right shows a very unique doublet feature. Hematite and goethite are iron oxides with their own features. And you can use these approaches, these spectrum fitting approaches, to form maps like Roger Clark did here. This is Lake Mead, and you can see that all of these rocks that more or less just look like various shades of brown to our eyes are actually extremely diverse in the infrared. This map is of the same area, but highlighting the 2 micron minerals, that is calcite, dolomite, illite and muscovite, gypsum, and others that we can all detect in this very constrained geographic area. So one of the things that we're discovering from the EMIT mission as we start to build these maps globally is just how incredibly mineralogically diverse our planet is, and how beautiful it is when you have this ability to be very, very precise and quantitative about the material components that are present in every pixel. Here's another application. This is some work showing Joshua Herringmeyer's work where he looked at total suspended sediments in the water column. So apart from phytoplankton, like PACE is doing, we can look with higher spatial resolution instruments at inland water bodies. This is from an airborne imaging spectrometer showing how you can fit the spectra of these water-leaving reflectances to estimate the composition and concentration of different particles in the water column. And here we have really elegant total suspended sediment map of the outflows of the Atchafalaya and Wax Lake Delta areas of the Mississippi. Another question was asked about the depth to which we could measure. So here's a similar analysis looking below the surface. After you've got the water leaving reflectance, you can try and estimate the water absorption and scattering properties, just like another atmospheric correction, to get at the benthic reflectance, that is the reflectance of the bottom of the ocean surface, down to about 10 or 15 meters, typically with airborne instruments. And then, of course, your mileage will vary with space-based instruments depending on signal to noise. And this allows us to fit models to the bottom reflectance and estimate, for example, the presence of coral, algae, and sand. This was done during NASA's coral campaign in the 2016-2017 timeframe, looking at Kaneohe Bay in Hawaii to try and understand the condition of these reefs. Another important science application area that's growing is hydrology, looking at snow melt rates. This is work by Nicholas Bone, looking at different kinds of snow grain sizes, which can be used to infer the broadband albedo, which controls the rate at which snow melts, and consequently outflow to reservoirs and ultimately water use implications. For all of these science questions that I've been talking about, spectral fidelity is really important. And here we've come a long way. And Hyperion was kind of a pioneer in this respect. It was NASA's first orbital imaging spectrometer in the visible shortwave, launched around the 2000 era. But this slide shows just how far we've come with the latest generation of imaging spectrometers, with improvements in both calibration, on-orbit stability of the instrument, uniformity, atmospheric correction, and all of these incremental enhancements over time have really gotten us now to the point where we're acquiring spectra that are in many cases comparable to what you might acquire with a field spectrometer from the surface. So we're really proud of the EMIT spectral quality, and it's a continual effort to fine-tune the calibration and to update, and we still have a long way to go. But really, being able to produce a high-fidelity spectrum with good signal-to-noise and minimal distortions and artifacts is really key to the ability to do all of these applications that I just mentioned. Okay, so now going on to EMIT in particular, I'll tell you my EMIT story. So EMIT is, of course, designed to look at properties of the mineral dust forming regions. Dana mentioned this briefly, and this image here really encapsulates the EMIT mission. So here we have a couple of different mineral dust plumes off the coast of Libya, and you can see that the composition of these dust plumes, that is their color here, really depends on the source mineralogy. So this red area is emitting a lot of iron oxide laden dust, and this area is emitting dust that has another optical character. And really these have two different effects, most probably in our climate system. The iron oxide laden dust absorbs a lot more solar radiation. And then this other brighter dust will probably scatter radiation back out into space and have a net cooling effect on the planet. So in order to really understand this process, we really need to know the mineralogy of the surface that generates the dust. So EMIT's mission was really a geologic mapping mission to understand the composition of these dust-forming regions, the minerals that are present there, so that Earth system modelers could then make better predictions about the kind of dust that would be emitted and the resulting climate impacts. And this, you've seen this image before, but just to drive the point home, we're doing this from the International Space Station, looking not just at dust-forming regions, but also at adjacent lands, so that we could run the clock forward on climate change and see if different lands became desertified in the future, how that would impact dust emission based on the mineralogy of those areas, and would it be a net positive or negative climate forcing feedback. So in order to do this, we designed a spectrometer that's called a Dyson spectrometer. This is an optical layout. If you're not an optical engineer, don't worry. The takeaways are that it's very simple, just a handful of optical elements. The light comes in through a telescope, is imaged onto a slit, diffracted off of a grating, and then imaged onto a focal plane array that sits here. The fact that it's such a simple optical system means it's simpler to align, and it also has very high optical throughput. It's a very fast spectrometer, which means it conveys a lot of photons for high signal to noise. And it's simple in other ways too. We don't have any onboard calibrators, for instance. So we tried to keep the build as simple as possible, focusing on making the instrument as thermally and mechanically stable as we possibly could, so that we could calibrate it once and then continue to use that thereafter. And so far, that approach has served us quite well. So this is what the CAD drawing looks like of EMIT. You can see the telescope here. There's the Dyson spectrometer in this enclosure on the left side. Below the optical bench is a bunch of electronics controlling the crowd coolers that keep the spectrometer at very tightly controlled temperature-wise. The focal plane array also has to be cryogenic, so that makes for a bunch of really complicated thermal subsystems. And it also does the data handling and compression, cloud screening, that sort of thing. This is the enclosure. This blue box represents a thermal shield that insulates us from the International Space Station thermal environment and also rejects heat out into space. This is what it looks like in the lab. So you can see here the technicians working on building the instrument. The aperture is facing us now, but it has some mylar foil over it for protection. But if it weren't there, you could see into the telescope, and there's the spectrometer at the very back. So this thing is actually pretty big. It's about the size of a good-sized piece of furniture, and it was pretty heavy. We packaged that up and put it in the back of a Dragon SpaceX capsule going to the space station. Here it is, this white box here. And then launched in 2022 in July, about 3 years ago now, to the space station, where after a harrowing couple of weeks, it was installed onto the space station by the robotic arm and started operations. And we've been operating more or less with a few minor technical interruptions ever since, collecting data over different parts of the globe. We're stuck in a nadir pointing perspective, so we basically just turn on the instrument whenever we fly over something of interest. This was our first light image when we first turned the instrument on. I hope your screen conveys just the detail that this contains. It's really awesome to think that we have a full spectrum of information for every one of these pixels. And this is over Perth, or a region near Perth, Australia. We took a look at the spectra and we saw all of the water vapor features, also liquid water in the this blue spectrum here. This is all exactly where we expected it to be. So at first glance, the spectra are looking very good, but we wanted to be more quantitative about that. And so the next step was to fit physics-based models to these absorption features to try and understand our wavelength calibration and if it had shifted after launch due to gravity unloading or g-forces experienced during launch. We wanted to confirm those laboratory measurements that this wavelength scale was still correct based on our knowledge of where these liquid water and water vapor absorption features should be. This was the result. So you can see we had very little wavelength shift. I'm plotting it as a function of cross-track position. This is really important. Those of you who've worked with imaging spectrometer data before may have heard of this concept of SMILE, and that basically refers to cross-track non-uniformity. Ideally, you want every position in a cross-track direction to have the exact same calibration, wavelength calibration. If they don't, it means that the spectrum you measure at one location is slightly different than the spectrum you measure at another, and it becomes very difficult to apply algorithms uniformly across the full image. EMIT's spectral SMILE, that is the deviation from a straight line, is within a couple of percent, which is just fantastic. That's right where we wanted it to be, and it means that for most analyses, you can assume that there's simply one wavelength calibration that holds everywhere. There's one other feature of this diagram that's interesting. Initially, when we launched, we had a slight tilt, and that's the red line. You can see that the wavelength calibration is shifted up a little bit on the left side relative to the right. And that's probably because of some minor change that occurred since laboratory calibration and on-orbit turn-on. But we were able to modify that by adjusting some of the temperatures of the focal plane array mounting components by just enough that the components moved by a few microns, and it actually adjusted our alignment. And that's the blue line. Just to give you an idea of the scales involved, if the spectrometer were the size of an American football pitch, then this adjustment would be about the width of a piece of paper. So really tiny scale adjustments in the alignment of all these different components, but that's really necessary if you want the best possible spectral performance from your sensor. After that, we did some vicarious calibration. So because we don't have onboard calibration objects, we used surface measurements of features like bare soil playas. This is from Ray Coakley's work in the US Southwest. We would use a model to project that reflectance to what we should measure at the sensor under prevailing atmospheric conditions. That's the radiant spectrum. Then we can compare that to what we believe we measured, and then that gives us a difference that we can use to update our radiometric calibration and update the vertical scale for this radiant spectrum. And then, of course, the real kicker is, does it apply? Does that calibration generalize to other areas? Work by Willow Coleman, looking at a wide range of different playas throughout the US Southwest. These are pretty stable, well understood optically. Found that yes, the EMIT instrument was obtaining accurate reflectance measurements at all these locations, or at least within the errors of the in situ and remote measurements. So this gives us confidence that the spectra are of good quality up to the uncertainties reported. Here's an example of the signal to noise, which is another kind of error that you could have. So a question was asked earlier about noise in imaging spectroscopy data. There are different sources of noise on different time scales. Miscalibration can cause errors, but they generally tend to be systematic over time. Atmospheric correction can cause errors that are more or less unique to one geographic location and time, right? But within a scene, they're probably systematic. And then this is the most transient kind of error. This is the instrument measurement noise that you experience just from the sensor itself, due to the analog to digital conversion, due to counting a finite number of photons. You have statistical, what's called photon shot noise. And so this random noise gives you a signal to noise that describes the precision of the radiance measurement. And that is, for our reference case, in the peaking at around 600, but closer to 200 to 300 in the shortwave region of the spectrum. This is in excess of maybe by a factor of 2 of our requirements, which means we're pretty happy with that result. Okay, then we take those reflectance measurements and turn them into mineral maps. This is Roger Clark's work. You can see in this spectrum plot that we're fitting different reflectance curves with minerals that we have in a library. And that gives us the abundance of a mineral, at least in a spectral sense. And then we use various intimate mixture assumptions and radiative transfer models to translate that spectral abundance into a mass fraction estimate. And we have to make other assumptions about things like grain size there. So this is very much a research area, but we are also now distributing these mass fraction estimates, which is really what the Earth system models want. Here are the initial mineral maps. Dana showed you an example of this before, so I won't belabor it. Suffice to say, these are the first real continental scale mineral maps of Earth's surface in the arid regions. And we're expanding out now to other regions of the globe now that we've completed our primary mission. Here's a movie by Paul Jeannot, who's actually ingested these results into an Earth system model and is now able to predict dust composition using the mineral maps that EMIT provided. So we have other modelers at Cornell as well, Natalie Mahawal's group with Longley Lee, Ron Miller at GIST, who's also they're also ingesting these EMIT measurements into their models. So it's a really exciting time for us because we finally get to see the outcome after a couple years of operating on orbit. And this is our current coverage. So if you're wondering whether these measurements are relevant to you, we've got very deep coverage over most areas of the globe, in some cases maybe 50 or 100 times in certain latitudinal bands, and are gradually filling in the gaps that remain over places like Amazonia, Sub-Saharan Africa, Southeast Asia. Pretty much anywhere the ISS goes in between plus or minus 52 degrees latitude. And there's a QR code with a link to our data. Okay, now quickly, I'm going to go on a quick deep dive into atmospheric correction. There are some questions asked on this, and it's important to understand. So atmospheric correction is the process of taking our radiant spectrum and inferring the reflectance that gave rise to that. So why is this hard? Well, first, let me talk about what is the definition of surface reflectance. And in order to define a surface reflectance quantity, we really need two things. We need to define the incoming and outgoing rays of the photons that we're counting. And here's an example of what EMIT measures. So this is the hemispherical directional reflectance factor, which is different from like an albedo, where one measures all of the incoming and outgoing radiation. That's known as a bihemispherical reflectance factor. We can only measure reflectance from the direction of the sensor. But really, reflectance looks different if you measure from different directions. Imagine looking at a specular, glinty, like say leaf or plastic or some other glinty object. It can look brighter or dimmer depending on the direction from which you look and the direction of the illuminating photons. And we can really only measure one direction at a time. So what we report is this directional reflectance factor. Somebody asked about BRDF previously. EMIT does not do any BRDF adjustments. Sometimes remote sensing analysts will try and modify this directional reflectance factor in order to simulate what we would have observed from some normalized observation geometry, like to try and put the sun and the observer in some new locations to make it more easily comparable with other overpasses. We don't do that because it's really fraught with all sorts of discipline-specific assumptions that may not work for everybody. So instead, we just distribute these directional reflectance factors and try to do as good a job we can of that. And then anybody who wishes can then use that to model other directions if they so desire. Okay, so that's one important ingredient of a reflectance. What else do we need to know? Well, the other important ingredient is the surface that we're measuring. Real surfaces can be very complicated, as you see from this image here of a forest canopy. And there's lots of multiple scattering going on. So photons will bounce from one leaf to another before they go back to the sensor. So it's really a fool's errand to try and measure all of the materials within a pixel. What we're doing is we're saying, here's a virtual polygon floating in space, and we're going to measure the reflectance of that polygon. And then it's up to the user to then interpret that and its relationship with any in situ measurements that they choose to make. So for EMIT, at least historically, that virtual polygon has been aligned with the geoid. That means it's perpendicular to the gravity vector. So it's basically flat at whatever elevation the surface is located at. In the future, we hope to move to a polygon that's aligned with a digital elevation model, so a tilted surface, right? And that's important because if you assume a tilted surface, it can actually affect the color of the downwelling illumination. If it's tilted towards the sun, it tends to have less blue sky illumination and more direct energy from the sun. This is a relatively minor effect for most observations, but it's worth knowing about. Regardless, if you look at the historical EMIT catalog, you will see reflectance is reported of a polygon that's more or less pixel-sized and aligned with the geoid. Each pixel really, in reality, has a Gaussian-like spatial response function, but we can ignore that to first order. And that's what we deem our reflectance to be. Now, if you are measuring a playa, like a flat surface, then the measurements that you make in situ are actually going to be pretty well aligned with that assumption, right? Because it's a broad, flat surface that's relatively homogeneous. And so that's why we use features like playas for our validation, because there we can make stronger claims about the expected alignment of the in situ and remote data. But if what you really care about is leaf properties in an environment like the one portrayed here, then you'll have to really pay attention to that difference in the two quantities that you're trying to, both the one that EMIT provides and the one that you're truly aiming for. Okay, so why is atmospheric correction difficult? It's because it's an ill-posed problem. So here is an example of what we call a Ford model. This is a radiative transfer model that describes photon transport through the atmosphere. And here, this mathematical definition starts with a state vector of free parameters that include the surface reflectance in every channel and the atmospheric parameters that we care to estimate, typically water vapor and aerosol optical depth. We're also looking at retrieving carbon dioxide as well, and also any instrument parameters that you care to vary during the retrieval. So we can then take these state vectors and, using our radiative transfer model, predict what the radiance at sensor would be using established principles of physics. Basically, set of differential equations that you solve to understand how photons would traverse through an atmosphere populated with gases and particles and so forth, and then back to the sensor. So this is pretty straightforward, or at least we understand how to do it. But note that there are more state vector elements than there are measurements. So there are more unknowns here than the measurements that we're making, than the channels of the spectrometer. What we really care about is the inverse problem, that is taking the radiant spectrum and trying to figure out what is the most likely configuration of state vector parameters that gave rise to that radiant spectrum. This is mathematically underdetermined, so we have to bring some new constraint to the problem. So we want to fit the radiant spectrum with some constraints that make it well posed and drive us to a unique solution. So if we're Bayesians, then we might try maximum a posteriori solutions. So this is Bayes' rule of probability. We want to maximize the probability of the state given our measurement, which decomposes this way, just by laws of probability, to the probability of our measurement given our state times the prior probability of the state. We ignore the denominator here because the probability of the measurement doesn't matter. The measurement's already been made, and it's constant for all states that we might want to consider. So this probability of X is our prior that we can use to express constraints about physically plausible state vector configurations, right? So if you have background knowledge about what legal surface reflectance spectra look like, or about what likely atmospheric conditions are, we can encode that in a prior distribution before we even make the measurement. And that actually is sufficient typically to drive us towards a unique solution. That soft statistical constraint makes the problem well posed. So this is the equivalent cost function to our maximum a posteriori solution. It has two terms. Basically, if you take the logarithm of the expression on top with multivariate Gaussians, you get the bottom expression. So our cost has a squared error term, which is our models matched to the measurement, which is the forward model prediction of X minus what we actually measured, right? So that's our residual. You see it twice because it's a squared error. And it's also weighted by this S epsilon matrix, which is an instrument noise term. So we're basically dividing by the measurement noise. Here on the right side, you see our prior distribution. So we're penalizing state vector configurations that depart too much from our physical knowledge about what legal surface reflectances should look like. So we have to solve this iteratively. There's no closed form solution. So typically what we do is we'll start with an initial guess. Here I've portrayed it as a 2D field with surface and atmosphere parameters. And this is the posterior probability on the vertical dimension. And so we're climbing some surface. At every iteration, we take the derivatives of the cost with respect to our current estimate of what the state is. That gives us a change that we can use to update our estimate and eventually converge, typically in just a handful of iterations. Now, this also allows us to calculate the uncertainties. Once you've reached this converged state, you can ask the question, well, how might instrument noise change this result? So this is one way to express that mathematically. This S hat is, you can think of it as like a Gaussian distribution, probability distribution in high dimensional space that represents our posterior uncertainty. The only random variable we're counting, though, here is S epsilon. That is our instrument noise. You can plot the marginal distribution, essentially the error bars on each channel independently, and you get something that looks like this. Do you see the error blow up in regions of the spectrum with very low signal, as we would expect it to? However, there's also a degree to which this would understate the true errors in a spectrum, because there are lots of systematic errors related to calibration and model discrepancies in our atmospheric model that this doesn't necessarily capture. So if you see the EMIT uncertainties that we distribute, just know that that's what that is. This is the uncertainty that we would expect in the state vector due to natural measurement noise from the sensor, but there also may be systematic uncertainties or other modeling errors that are not accounted in this uncertainty. Of course, doing so is a long-term research project, and we're hoping to bookkeep some of those other errors in S epsilon in the future, so that we'll be able to do a better job of predicting the true uncertainties. Okay, so here's a visual example of what this atmospheric correction looks like. This is a really compelling case that Phil Broderick published in 2021, where an imaging spectrometer overflew a wildfire. You can see the smoke plume and the radiance data. By fitting models to each pixel independently using the approach I described, you can decompose that into the surface signal, which is the surface reflectance under the smoke plume, and then this is the thickness of the smoke plume expressed as an aerosol optical depth parameter. So this is kind of an extreme case, but it's what we're doing globally with the EMIT mission to produce those level 2 surface reflectance products. Okay, now I'll just take a couple of minutes to talk about the future of NASA imaging spectroscopy. EMIT's a really powerful instrument, and it gets better every day as we continue to refine the calibration and analysis. We have a bunch of great updates coming briefly, I think, for the surface reflectance in particular, that I think will really help things even more. But what about a few years down the road, looking at the next decade? What can we expect from global imaging spectrometers? One example of this is the Surface Biology and Geology mission. This was proposed by the NASA Decadal Survey in 2018, and it exemplifies a global imaging spectrometer at 16-day revisit, so about 10 times the data rates of EMIT, so that we can observe a much wider range of science questions and features related to changes over time. Things like the phenology of vegetation or water resources with melting snow, things that you can really only measure when you have a pretty regular measurement every couple of weeks or so. Of course, it will go beyond EMIT's latitudinal restrictions. So we'll be able to image areas of the Arctic too. We'll be able to look at mineralogy in Greenland as the ice retreats. There are lots of things we'd be able to do with a polar orbiting sensor of this kind that we can't today with EMIT. So this is a really exciting possibility, one that we're actively pursuing. And of course, it would provide lots of different application benefits from everything from critical minerals, surface geology, understanding environmental hazards, in particular wildfires, where there's a real lack of understanding about fuel conditions now. Our ability to measure non-photosynthetic vegetation every couple of weeks would be a real boon to fire prediction, fire risk prediction. Water quality and aquaculture, agriculture, food security, water resources. They're really just as a huge raft of different possibilities. And I want to close with this one slide to drive home just the real difference between spectroscopy and multiband imaging. So multiband imagery is super powerful for a lot of different applications, but there's a real difference in the way that we go about working with multiband data versus spectroscopic data. Multiband data often has good correlations with the parameters of interest that one's interested in sensing. However, spectroscopic data is really, it's an analytical technique. It lets us fit physics-based models to the spectra that we measure and be very, very quantitative with error bars about how much of the materials is present, and really dive down into discriminating much finer degree of different species than we would be able to using multiband data alone. As you can see here from the mineral maps showing just the astonishing mineral diversity apparent in spectra, everything from rare earth elements to iron oxides to alteration minerals. And it really just doesn't appear in the multiband data. So not only is the data of a qualitatively different kind, but the analysis that we use, the ways of looking at the data, and the ability to do quantitative retrievals is really quite different in the two cases. So I'm really excited both about the future of EMIT as it continues to operate on the space station and produce incredible data, but also the future of imaging spectroscopy writ large. And with that, I'll thank you all for listening to the talk and take any questions that you might have. Feel free, if there's material you didn't understand or you want to follow up on items, to send me an email and launch discussions offline. I'm more than happy to field those.
Okay, thank you, David. There was actually a question that was asked earlier on, and I wondered if I could pose that question. It was an ECOSTRESS question. Is that okay?
Of course.
Okay, so the ECOSTRESS question is, could ECOSTRESS be maximized to monitor or model water use in specific areas around the U.S. and Africa in terms of water resource research efforts?
Yeah, that's a really good question, and something that I've asked some of my evapotranspiration modeler colleagues about before. I think there's probably potential there, probably to improve assumptions about maybe the state of vegetation, or if, for example, if you make certain assumptions about crop type, you could imagine a visible shortwave infrared spectroscopy providing more detailed information about the vegetation that could inform those evapotranspiration models. I'm not an expert in that field, so I might defer to Glenn on just how useful that would be. But I think there's probably potential there. Yes.
Okay, thank you, David. I'm just scanning for. I see they can respond. I'm just making sure that All right, why don't I start from the bottom up here? Regarding mineral mapping, have you used an IMAP-based other physical modeling method to model specific mineral signatures? I've been thinking about modeling minerals, as is the case with the methane carbon dioxide spectrum for a given scene.
Yeah, I think there is there's a bit in that question that I want to unpack. So we do use physics-based modeling approaches to map minerals by fitting the reflectance spectra with library mineral signatures. It's not currently an IMAP, that is an iterative maximum a posteriori approach, because in those cases, it's generally a well-constrained problem. So if you, the number of minerals that we care about in a certain wavelength range are fewer than the number of distinct measurements that we have. And so it can be a simpler sort of least squares. Of course, IMAP with an unconstrained prior just reduces to least squares anyway. So I guess in that sense, it is a form of generalized iterative maximum a posteriori. So I think there's some nuance there in exactly how we do that model inversion, but fundamentally it is still a physics-based model inversion. When we go towards intimate mixtures, things get a lot more nonlinear and complicated, and there I think something like IMAP or Monte Carlo-based retrieval approaches would be critical.
Okay, thank you, David. The next question is, let me go up a little bit here. For EMIT level 2B, any suggestions for applying topographic, BRDF, and glint corrections if needed for our application?
Yeah, I think that so the emit reflectance is level 2A, and then level 2B is typically the mineral product. So I assume the question is, if you want to use the reflectance for your own application, what topographic or BRDF adjustments might you want to make? And I think that's really a call. It's going to be very specific to what you want to use it for. A lot of the vegetation community likes to do topographic and BRDF adjustments to the data to make it more homogeneous, to remove the influence of slopes on the apparent reflectance. Similarly, in the aquatic realm, I think glint correction is really essential. You'll want to take the water-leaving reflectance that we distribute and then remove the glint to get it something closer to a water leaving reflectance, or I'm sorry, a remote sensing reflectance like an RRS. We are likely to have the ability to produce those in the near future. So we are upgrading now our radiative transfer models with the ability to separate different diffuse and direct downwelling components so that we can incorporate topography and also do glint correction to the emit data. So it's quite possible that this will become available shortly. If you're really interested in that, please drop me a line. BRDF correction will probably not be done for the foreseeable future just because it is so discipline specific.
Okay, thank you, David. We probably have time for one more question before moving on to the next speaker. On the initial mineral map, there seems to be the less data across the equatorial latitudes close. Is it safe to assume that there are no minerals captured by EMIT?
I think that this question is referring to the global mineral map that we showed, and I should explain better where that comes from. So initially, the EMIT mission had a target mask that encompassed the mineral dust forming regions of the world like Northern Africa, but it left out big chunks of the world too because we didn't believe that mineral dust was being emitted from those regions. And so the mineral maps were a little bit patchy, and there are areas where we just didn't acquire data. We're now since the EMIT primary mission ended, opening up our target mask and acquiring data pretty much globally within all the places that the ISS travels. So we should be seeing those gaps start to close. But that's why it didn't appear in the initial mineral map.
Okay, let's try to address this one last question, actually, that was asked earlier on in your talk. I would like to check how Dr. Thompson, if he could go over how residual values are defined when he mentioned in the slide about accuracy fidelity as a key for the reflectance signatures.
Yeah, indeed, there are many different kinds of errors. And so in that one image that I showed, there was a residual plotted, and I would refer you to the original SPIE paper for the precise definition. But I think more generally, it's important to recognize that there are systematic errors. And if you open up any imaging spectrometer data cube, it won't take you long to find all of these. All right, there are systematic errors caused by calibration and atmospheric correction, spikes in the near infrared, maybe from water vapor absorption that isn't quite corrected perfectly. And then there are random errors that you'll see just from one pixel to the next based on, photon counting and other error sources like that are quite transient. So I think part of the challenge that we face in uncertainty quantification is to tease apart these different error sources and bookkeep them properly. We're good at understanding our instrument noise. The other more systematic stuff is far more challenging, but it's really in wrapping our arms around those sources that we really improve our understanding of the system and improve it over time.
Okay, thank you, David. And with that, I would like to transition to our next speaker this afternoon, Glenn Hulley, who is going to, excuse me, speak to the fundamentals of thermal infrared, remote sensing theory, retrievals, and science. And so with that, Glenn, I'd like to toss the presenter role over to you. It looks like you've already ready to go. Thank you.
Thank you. Assuming everyone can see my slides.
Yes.
Okay. So moving on to the longer portion of the electromagnetic spectrum into the thermal infrared. My outline here is I'm going to give some broad background on thermal infrared, the theoretical basis behind what it is we're actually measuring in the thermal infrared. We'll then go on to some details of how we retrieve our two fundamental quantities here in the thermal infrared. This is the surface temperature and the spectral emissivity. I'll go over some validation showing users what they can expect in terms of accuracy with these two products in the data. And then I'll go through some really high-level examples of various different types of science and application users of the data. Christine has already gone through some of those, and the actual use of the more technical use of the data will be covered this afternoon with Eric and the LP DAC. I would also like to say there's a plug here for me is that a lot of this information and even more detail about these topics is covered in this Taking the Temperature of the Earth book that we published with our European colleagues a couple of years back. And it really is in-depth look at thermal infrared retrievals across all different domains of the Earth's surface. Okay, so in terms of science and applications uses of the data, it covers a real broad range of different interdisciplinary science. We like to sometimes call it the Swiss Army knife of Earth surface science in terms of the thermal infrared data usage. For example, in using the LST in hydrological models, we can estimate water consumptive use in managed agricultural systems, such as this evapotranspiration plot you can see on the top left. The LST, the land surface temperature, and the sea surface temperature can be combined to monitor climate trends over about a 25-year period now from MODIS and AIRS. And then the more fine-scale thermal data from ECOSTRESS and ASTA can be used to quantify the small-scale variability within urban heat islands in cities. The emissivity in itself is also particularly useful for a number of different earth science uses, including monitoring land cover, land use change, in geology, mapping silicate minerals, and then surprisingly, it's used extensively in data assimilation and atmospheric water vapor retrievals from sounders such as AIRS and EASI, and this is because they need to initialize the energy balance at the surface in order to model what they're retrieving at the top of atmosphere. So just to give some general situational awareness of the region that we're in here in terms of the electromagnetic spectrum, David just really went nicely over the UV to near IR into the visible shortwave infrared region, which is more common, I guess, to a lot of users and scientists out there. In the thermal infrared, we focus more on this longer wavelength region around 10 microns, which is an area where the Earth's emitted radiation is at a maximum. And this usually occurs typically around 288 to 290 degrees Kelvin. And in this region, there are two atmospheric window regions. One falls at around 8 microns, and then the longer one falls at around 10 to 11 microns. And it's these regions where the thermal radiation is largely undisturbed as it travels from the Earth's surface up to the top of atmosphere into your sensor, and so requires minimal atmospheric correction and correcting of the data to be able to use it to estimate the surface temperature. So in general, it's 8 to 13 microns, and most of the observations we have from space right now are multi-band instruments. So in the thermal infrared, it's really important to understand that what we're seeing on the left here, as an example, is an airborne image in terms of its brightness temperature, which is just an inversion of the radiance. We're seeing a combination of a signal from both the temperature of the surface and also the spectral emissivity of the surface. And the emissivity of that surface directly relates to the actual composition of the surface. So this is a really nice example showing that here. This is the Occitan cross in Toulouse Square. It's made of brass and copper that's inset into the pavement. And so if you're walking along this area, it's kind of tough to see. You can kind of see it there, but it's generally kind of invisible. But in the thermal infrared, it really stands out because the brass has a different composition to the surrounding paved concrete, and also it's at a different temperature. And so with the thermal infrared, we can really see those type of features really clearly. Oops. So starting off with the Planck function and its relation to temperature, what we're actually measuring is the amount of radiant energy that any surface emits from this above absolute zero in terms of its temperature. The Planck function is dependent on wavelength, but also the surface temperature. And to retrieve the temperature or the brightness temperature from this measurement, you simply solve for temperatures in this equation, or what sometimes we say is inverting the Planck function. Now, if we were to plot this function for different temperatures, you'd see that in the 8 to 12 micron range, you can see they range from about 250 degrees Kelvin to about 330, which are the very typical Earth-like temperatures that we experience on a day-to-day basis. So this is about minus 30 to plus 70 degrees Celsius. And so it's really in these wavelength ranges that we want to utilize those features in order to accurately retrieve those Earth-like temperatures. Also notice that as the temperature increases, the maximum of the Planck function moves to lower and lower wavelengths. So at around the mid-infrared region, about 4 microns, you can see at about 800 degrees, the maximum goes at around 800 degrees. So it's this region that's really useful, for example, in monitoring high temperature features from fires, lava flows, and other volcanic activity. And in fact, many sensors have bands and detections in that range, especially for those different types of high temperature science use and applications. So then what is emissivity then? If we know what the radiance is, for example, on the top right plot here, we can see we've plotted the radiance of a black body. This is with the assumed emissivity of 1 at about 300 degrees Kelvin. But if we plotted the same radiance of a different type of material, for example, quartz, which has a very specific feature here between about 8 and 10 microns, called the quartz ristral and band, you can see that they're quite different. And so the emissivity of this quartz material is simply derived by taking the fraction of the radiance of the material to that which occur from a black body at the same temperature. So that's what you see at the bottom right here is the extraction of the emissivity from that radiance spectrum. And the emissivities typically range from roughly 0.55 to about 1 in the thermal infrared range here, from 8 to 14 microns. This is a number of spectra of different materials from the ECOSTRESS spectral library that's freely available online. You can see that they range. We have a very wide range in emissivities in the 8 to 10 micron range, consisting of silicate minerals and feldspars and other rock forming minerals and materials. There's also a very specific feature at 11.3 micron, which is from carbonates. But in general, unlike in the VSWIR, if you look at the green lines here, this is a vegetation, water, ice, and snow. These are gray body surfaces. They have very little variation in the thermal infrared. And so it's mostly these sort of barren rocks, soils, and sands that are of most interest in terms of composition in the thermal infrared. And this is demonstrated really nicely in this example on the left. What I'm showing is the emissivity of different types of igneous rocks, and they're all offset for clarity here. And you can see that the minimum emissivity along the spectra of these different materials falls to higher and higher wavelengths as they move from more felsic, which is minerals with more silicate and framework silicate content, such as quartz, to more mafic types of minerals, which are more volcanic rocks. Think of basalts, darker rocks. And you can see the actual spectral variability actually decreases as well as you go to higher and higher types of mafic rocks. And then we can use this information in models to estimate, for example, the weight % silica in any given pixel from remote sensing data. This is an example of the Aster estimated weight % silica over Northern Africa, ranging from about 50 to 80%. So the lighter yellowish orangey colors here are pretty much the sand dunes of the Northern Sahara where quartz and feldspars and other rock-forming minerals are ubiquitous. And then the darker pinker colors here are extinct volcanoes, volcanic rocks, and other mafic types of surfaces. So getting back to modeling what we're actually measuring here, this is the thermal infrared radiative transfer equation. It's composed of 3 different terms. So the first term here is the basic surface emission. So this is a quantity that's dependent on both the emissivity and the temperature of the surface, and accounts for usually more than about 90% of the signal that we receive in the thermal infrared. We then have the surface reflection term. This is the radiation from the sky that is actually emitted down towards the surface and then reflected back up into the direction of the sensor. And then lastly, we have the atmospheric emission term, which is the radiation that's directly emitted upwards into the path of the sensor. These are generally pretty small and depend a lot on the atmospheric humidity for the observation. They're generally less than about 10% of the total thermal signal. So then to extract the emissivity and the temperature from this equation, we first need to remove these atmospheric variables. These are the transmissivity, the sky radiance, and the path radius. And these can be determined quite easily from radiative transfer models such as Motran, RTTOF, CRTM. There's a bunch of them out there. And combined with atmospheric profiles that include air temperature, humidity, geopotential height, and so forth. And then once those are removed, we can estimate the surface radiance and then expose those emissivity and land surface temperature signals that we're directly getting from the surface of the Earth. To do that, we use multi-band instrumentation from thermal infrared sensors up in space primarily. For example, from 2000, we've used Aster and MODIS on the Aqua and Terra platforms. So Aster, for example, has 5 bands that cover the 8 to 13 micron thermal infrared range here, shown in blue, and MODIS has 3 bands here shown in green. ECOSTRESS, which was launched later on in 2018, has very similar bands to Aster that combines information from both Aster and MODIS together. And you can see that all of these bands fall in what we call these atmospheric window regions, where the transmissivity is at its maximum and the amount of atmospheric correction we have to perform is at a minimum. So we avoid these strong water vapor regions here below 8 microns, the ozone classic absorption at around 9.6 microns, and then the longer absorbing water absorption regions above about 12.5 microns. Now, in terms of actually retrieving those 2 quantities, it's a rather difficult problem because it's an ill-posed problem. We have to solve for both the temperature and an n number of emissivities depending on how many bands you have, whereas you have only an n number of observations, which are radiances, and so it's an ill-posed problem. There's been a number of methodologies put forward over the last 2 decades to solve the problem. One of them on the left is probably the most common currently. It's called the temperature emissivity separation algorithm. It was developed for Aster in 2000 and now is applied to both MODIS, VSWIR, and ECOSTRESS LSTNE products. It retrieves the temperature and the spectral emissivity simultaneously. And it's pretty computationally fast, and it's well characterized in terms of its uncertainties. And the little trick that it uses here to solve this ill-posed problem is it models what the minimum emissivity is on a curve with respect to its actual spectral variation on that curve, so the min-max difference in emissivity on any spectrum. And this actually follows a really nice, mildly nonlinear curve, where vegetation, rocks and snow fall in this higher region, and more barren surfaces have more variability, so fall in this lower region. And this is what we can utilize to extract out that spectral information in the radiance data and be able to retrieve temperature and emissivity. A much more simpler version of this is called the split window algorithm. This has been used extensively, more focused on sea surface temperature retrievals, where the emissivity of the ocean is very well known. And what it does is it assumes a given emissivity based on some kind of land cover classification or a priori knowledge of the surface you're working with. And then it uses the difference between two bands, 11 and 12 micron band, to do the to account for the differential atmospheric water vapor absorption between those two bands. So it's a pretty simple to implement. It's computationally very fast. It does rely on simulations ahead of time to determine the split window coefficients. Now, the temperature and emissivity, although they're independent variables, so the temperature doesn't determine the emissivity and vice versa, they are dependent on each other in terms of the actual accuracies of retrieving them. So, for example, if you get the emissivity wrong in a retrieval, you're going to get the temperature wrong as well. And this is a sort of an extreme case example of this. This is the Mauna Loa caldera in Hawaii, which is a large basaltic solid surface. And for example, the split window algorithm for MODIS, here shown in blue, assumes a really high emissivity, which is incorrect when you look at the actual retrieve values from the TESS algorithm, here shown in red and in black from ASTER. And you can see it's about a 10% difference here in emissivity. And when we look at the temperature of that basaltic surface, you can see that the split window algorithm is roughly about 10 to 12 degrees different from the TESS result. And so large errors in emissivity do translate into very large errors in temperature. And so you really need an algorithm that's able to both retrieve the temperature and emissivity simultaneously. In terms of the split window algorithm, though, however, over oceans, it performs very well because we know what the emissivity of the ocean is. It's a very fixed and constant value in the thermal infrared. And so when we compare the standard ECOSTRESS, for example, land surface temperature product on the left, with the gold standard right now, which is the MODIS Aqua SST product, and then we compare it with the SST product from EcoStress on the right. This is a new SST product that will be available in Collection 3, upcoming towards the end of the year at some point. You can see that the biases are much lower. So the SST product is more stable and does a lot better at retrieving the temperature over water and other inland water body surfaces. Now, some new approaches in the thermal infrared are optimal estimation. While, as you probably saw from David's presentation, it's not new in a lot of other fields of science. For example, in atmospheric retrieval, atmospheric retrieval schemes, and also in ISOFIT and VSWIR retrievals. It's a pretty common approach to use currently, but it's never been implemented operationally for the thermal infrared. So with development of the SBG mission of the last couple of years, we've been testing a number of different algorithms in addition to the TESS algorithm. One of these is the OE algorithm, and it has been performing quite well in terms of comparing it to our other retrieval schemes. I won't go into too much detail here because I know David covered a lot of it, but it requires optimizing the cost function and solving for our state variables here, which are the X values, and then finally tuning differences between the measurement and error covariances. Here are measurement covariances on the left, that's the S sub A quantity there, and our a priori error covariances on the right, this is the S sub Y quantity. And here I've outlined what each of these variables mean and currently what we use in terms of applying data to be able to solve this problem. So the unknown surface state here is the LST and emissivity. The priors here, we use a combination of climatology data and also lab spectra data. And then the error covariance matrix is computed from a set of lab spectra that I showed you earlier, which is from the ECOSTRESS spectral library. And then the error covariance is from the instrument noise model of your specific sensor. In this case, we use the ECOSTRESS noise model. So I'll run through quickly here some examples of differences between the optimal estimation algorithm and the temperature emissivity separation algorithm. This is our heritage algorithm. These were run on simulations for mid-latitude summer atmospheric profiles. These are usually pretty difficult cases for the thermal infrared and over barren surfaces, so sands, rocks, and soils. So on the left, you can see the accuracy or the bias in the two different algorithms, OE in blue, TESS in red here. And you can see that they're pretty similar when you look at the errors with just the NE delta T, which is the instrument noise. And then if you combine the instrument noise with errors from the atmosphere, you can see that the biases are pretty low, down below about 0.2% in terms of emissivity. In terms of the total uncertainty, however, you can see that the TESS algorithm actually does slightly better than the OE when you look at both the atmospheric and the instrument noise errors combined. Now, moving to vegetation, water, ice, and snow, as I said before, this is an area where the TESS algorithm actually does have some problems and usually overestimates the temperature and underestimates the emissivity over these types of surfaces. And here you can see that the OE algorithm, in fact, does quite a bit better than the TESS algorithm, both in terms of the bias and also reducing the total uncertainty in terms of RMSE, as I'm showing on the right here. In fact, it brings the total uncertainty from about 1 degree down to less than about 0.2 degrees Kelvin. So this is quite nice to see in that it solved this issue that we had with the TESS algorithm of gray body surfaces. Another interesting aspect here was that this is an example of an ECOSTRESS seen over the Salton Sea and Peril Valley region. On the left is the TESS algorithm retrieval for a specific band for the emissivity. On the right is the OE retrieval. And you can see that the TESS algorithm is a lot more sensitive to actual instrument artifacts. For example, striping, band-to-band misregistration that we sometimes see on the edges of fields. Whereas in the OE algorithm, you can see it's a lot smoother result. And so the trick here is really to be able to balance that information content between your a priori estimate and the actual data and signal that you're getting from your instrument. We don't want to beat down that noise too much so that we just rely on the a priori, but we also want to, rely on the a priori a little bit to smooth over some of these artifacts that we sometimes see with thermal infrared instruments. In terms of validation, we have 2 automated validation sites that are run by JPL. They've been running continuously since about 2000. These are pretty much just radiometers that we have at Lake Tahoe and Salton Sea, measuring the outgoing radiation and then inverting that to get the temperature of the water surface. And then every time a satellite flies over, we do a matchup and plot that versus the in situ data, which is shown on the left here for the ECOSTRESS collection 2 data. And so what you can see is in terms of the bias, we have a bias less than 0.5 degrees for quite a wide range of temperatures, stretching from 275 to around 310 degrees. The total uncertainty here is less than 1 degree, which is generally what we aim for in terms of the total uncertainty of the measurement. And I'm not showing collection 1 here, but in collection 1, we had a 1 degree cold bias at our lower temperature ranges, which is now being corrected in collection 2 using a bias correction. Over hotter targets, such as our pseudo-invariant sand dune sites, these include a wide range of different sites covering a lot of different types of minerals across the southwestern US. Now you can see our temperature ranges all the way from 270 degrees upwards to about 340 degrees. And although we have a larger uncertainty, likely because of their higher temperature range, it generally falls between about 1 and 1.5 degree, while our biases and our accuracy in general still remain pretty good, less than about 0.5 degree Celsius. So those are the types of errors that you can expect when, in general, looking at ECOSTRESS land surface temperature data. When you're looking at the emissivity data, these are some very typical emissivity spectra that you'll see from ECOSTRESS. As you can see, it has 5 bands. And here we've simply matched up measurements made at each of these 3 dune sites where we acquire samples of the sand, bring them back to the lab at JPL, measure the emissivity in the lab with a spectrometer, and then directly compare that to the instrument ECOSTRESS retrieved emissivities in this case. And you can see pretty good matches here, both in terms of spectral shape and in terms of absolute value. Generally, they fall within about 1 to 1.5%, depending on the band. But this is expected because we retrieve the emissivity first and then the temperature. So if I'm showing you good temperature results, the emissivity results will directly fall out of that. Okay, then lastly, I will go over some pretty high-level examples of the use of these types of thermal infrared data, specifically from ECOSTRESS. ECOSTRESS was launched in June of 2018. In fact, this is almost our 7th birthday up on the ISS. We're located on this 10th station here on the GEMIF module. We were slated to only last about a year, but we've now gone on for 7 years. So I think that's pretty remarkable considering that it is a Class D mission and also consisted of a lot of sort of off-the-shelf commercial parts. So as you've seen probably from previous presentations today, ECOSTRESS measures the thermal infrared in 5 spectral bands at a 70-meter spatial resolution. The temporal resolution is variable because it depends on the exact precessing orbit of the ISS, but in general, it's about 3 to 5 days over the US with a higher repeat cycle as you get closer to the more northern latitudes around 40 to 50 degrees. As I said, the 2 fundamental science products here are the land surface temperature and spectral emissivity, and these are used in a wide-ranging different earth science and applications, which I will go over the next couple of slides. The primary and key use of the data, I'd say, would be in water resource management. For example, in estimating water consumptive use over managed systems, such as these agricultural fields here in Kansas City. These are fixed pivot primarily cornfields. But also it's really useful in monitoring drought impacts because we can, from the thermal signal, we can tell whether plants are under stress before we actually physically see the deterioration in the plant itself. And that's really important because we can get a sort of a precursor view to an impending drought in any given region, for example. ECOSTRESS, the ET or evapotranspiration is also used to optimize irrigation strategies, which I'll show in the next example. And in this case, we want to always maximize the crop per drop, as we always say. So in these 2 examples, you can see on the left, the blue fields here are high ET, so they're transpiring a lot, they're very healthy. And the more sort of beige greener areas are areas that are usually a bit drier or they're under stress. And so it's also interesting to see in this unmanaged landscape around these fields, you can see that in 2018 was a lot wetter than it was in 2022, where we see a lot drier surrounding landscape. So the 2022 region here in this example was probably had a lot drier here and a lot less precipitation. In terms of optimizing irrigation practices, IrriWatch is a really nice example of a precision agriculture platform that ingests a lot of ECOSTRESS data and also other sources of data, VSWIRs and other thermal infrared data. And they assimilate all of that data into their models, and then they're able to actually provide farmers through an app on their phones the morning that they're about to go out and irrigate and take care of their crops with information on exactly how much to water. So on the top right here shows an example in how much water was advised on this particular day in terms of millimeters. But also more importantly, we're able to provide spatial information on which fields to water more. For example, the blue field here was obviously under a lot of stress and needed a lot more water than the remaining fields. But also that resolution from ECOSTRESS, you can sharpen it down and we can get the within field variation as well of ET and how much water each of those within field variations require. Another really nice use of the data here has been demonstrated in coastal water temperatures. We'll often get a lot of coastal water temperature data from ECOSTRESS as the orbits traverse from the ocean over into the land. And we derive the products over ocean and water as well. So there's no, special formula for deriving it over the water. It's the same algorithm that we use. We will be implementing an improved algorithm in collection 3. But on the left example here shows a really nice example of using both ECOSTRESS and Landsat to monitor thermal discharge, for example, from this nuclear power plant in San Luis Obispo, which can have a real detrimental effect to the water quality, but also the marine life in the area. And when combining ECOSTRESS and Landsat, we can do this at almost every 2 to 3 days when you combine those two different acquisition schedules. And so that's really useful for monitoring that on an almost daily basis. On the right shows also a recent example from Jake Longenecker, who's with us this summer here at JPL, in fact, using ECOSTRESS to monitor these very fine-scale coral reef microclimates, which are really useful for not only identifying potential coral refugia, but also helping to predict coral bleaching in these vulnerable regions. And the ECOSTRESS data here you can see is almost 200 times more finer resolution than the typical grist products here, which are produced at about 1,000 meter resolution on the bottom right. Moving on to wildfires, I really like this example. This is from predicting wildfires in southeastern Australia. What this study did was they incorporated both ECOSTRESS data, but then also other types of vegetation index data, rainfall, topographic data. They input these into a machine learning model and then determined which one of those variables explained the actual fire that occurred the best. And what you see here is that it's actually the top 2 ECOSTRESS products here. This is the water use efficiency and the evaporative stress index, which had the highest prediction capability of explaining the location of these wildfires. The water use efficiency here again is the GPP over the ET. It's the ability of pretty much the efficiency of how plants use the water that they're given. So it's the gross primary production divided by the ET. And what they found was that they could predict more than 90% of all wildfire occurrences 1 week ahead in southeastern Australia and South Wales. So not only predicting fires, but actually monitoring their movements is also really important. So this was an example of the Bootleg fire in Oregon in early January. It actually occurred over an extreme heat event in this region. And you can see here that ECOSTRESS came over on the 10th of July, and we were able to actively map the fire front of this fire. And then over the 11th, we could see how it spread rapidly towards the northeast. And this is really important because, these fires obviously very often traverse across high voltage transmission lines, which are, of course, pretty dangerous in terms of igniting even more fires, cutting off power to people who are, relying on cooling during these type of events. And so this is really important for people on the ground, but also in knowing when to actually turn off these power lines during these fire events. Then moving on to urban heat, this has been a particularly useful and vital part of our mission over the last couple of years in monitoring fine-scale urban heat variability to help city local officials with their heat mitigation efforts, but also to give warnings on hotspots in certain regions in different cities. So this is a really nice example from our summer student Ashley Agatep at Chapman last summer. She was with us and she implemented a sharpening algorithm that we use here at JPL, which can get the data down to about a 10-meter resolution using Sentinel-2. And what she did was here, she overlaid this on a map of Phoenix streets and pulled out the temperature over these individual streets. And what we did here was we estimated the amount of time it would take to get a contact burn if someone fell on the street, for example. So you can see the red areas here reaching about 150 degrees Fahrenheit, it will take less than 3 seconds to receive a second-degree burn, which is kind of frightening. In fact, in 2023, when Phoenix experienced a July where every single day in July exceeded 110 degrees, there were roughly 140 odd hospital visits from people falling on the ground and receiving these contact burns. And 14 of them, in fact, were fatal. So it's really important, as you can imagine, for city officials to take a map like this and use it not only to help implement mitigation efforts, for example, in this area of Maryvale, which is a much poorer community in Phoenix, but also to warn people in certain areas, where they could be at the highest risk. So not only can we map hotspots within cities, but we can also quantify the effects of cooling and heat mitigation measures that cities have implemented. For example, in Los Angeles, Phoenix, and a lot of areas of the US now, they're implementing this cool pavement technology, which is literally a paint emulsion with higher reflective qualities than typical asphalt. And it's generally, when you measure it on the ground, it's roughly about 10 degrees cooler than regular asphalt. And so in 2018, they started a prototype project in the San Fernando Valley. And in 2020, ECOSTRESS demonstrated this really nice image where we could see a distinctive cooling along Stephanie Drive, which is this sort of circular street within the San Fernando Valley. And this image was, in fact, used a lot by the city to solicit more funding from California state, but also federal funding to expand and improve these cool pavement projects across the LA County basin. Again, in 2021 and 2022, we actually flew the same area with our airborne instrument, HITES. This is a hyperspectral thermal emission spectrometer that we get data at around 3 to 5 meter resolution. So we could really discriminate the very fine scale temperatures within the street itself. And we confirmed here, a couple of years later that with HITES, we could still see about a 7-degree cooling over Stephanie Drive relative to the southern street here at Skyros Drive. So it not only shows the efficacy of this method of painting the streets, but also its longevity, where it's already lasted about 4 to 5 years and it's still about 7 degrees cooler. And then the last example here I'll show is, moving away from the high spatial resolution to the more sort of high temporal resolution data from VSWIRs, for example. VSWIRs and MODIS have been flying since about 2000, acquiring thermal infrared data. And with this type of data, we can start looking at more longer-term trends and longer-term temperature impacts over different regions. For example, this is a really nice study that my postdoc, Shirley Yu, is currently working on, where he's looking at the correlation between the increase in nighttime temperatures and also the the urban expansion within the fastest growing Indian cities. So on the right here is an example of Lucknow. You can see how rapidly the urban heat island has increased just over a 10-year period from about 2013 to 2024 over the city of Lucknow. And this can be directly attributed to this urban expansion from low plants to more sparsely built types of urban types here, which we refer to as local climate zones. And we also hypothesize that this is also due to urban densification within the urban environment itself. And in fact, we see this nighttime warming increasing over a lot of different cities in India, and we'll likely be expanding this type of analysis to other cities of the world pretty soon. Then just to end off, what is the future of future high spatial resolution multispectral thermal infrared data? Well, this is just a schematic showing what is currently flying. So we have ECOSTRESS and ASTER here, which will end pretty soon in 2026 and 2028 respectively. ECOSTRESS we expect to be up there until the ISS is actually decommissioned. So that could be 2028, 2029, could be roughly in that time frame. There are 2 European missions going up pretty soon. One is Trishna, launching in 2026. That's a 4-band, 60-meter thermal instrument flown by Knez and ISRO. So that will be really good because it will extend the ECOSTRESS thermal data record once ECOSTRESS goes down. From NASA, we had SBG-TIR and Landsat Next. However, from the last president's budget, it seems that those are probably unlikely, although they could be delayed. We just don't have enough information right now. An additional instrument from ESA called LSTM will launch in the late part of the decade and may consist of 2 different sensors with a 50-meter thermal resolution with about 5 thermal infrared bands. So from about 2029 onwards will be really nice because we may have a near daily repeat cycle of high spectral resolution thermal infrared data. And that's, if Landsat is flying, Landsat 8 and Landsat 9 are still flying at that time, that would be even better. So I believe that's it. Yeah, that's all I have. Thank you very much for listening. And for the West Coast people, thank you for listening over your lunch break.
Okay, thank you so much, Glenn. So Africa, I know that we've got 5 minutes, I believe, until the next talk. So let's go ahead and jump into some questions here. All right, if you would bear with me just for one moment. Alrighty. Question asked, let's see. All right, is it okay for me to, let me make sure it's not been answered already. Just 1 second.
Many have been answered, but I think that there is a very good one, and maybe Glenn can elaborate more because I think this will be a recurrent question about ECOSTRESS thermal data and Landsat thermal data.
Yes, I did see that.
So maybe Glenn, you can expand more. I saw you have one slide about the comparison between the Landsat thermal and the ECOSTRESS thermal.
Oh yeah, sure. So Landsat 8 and 9 has 2 thermal bands from the TIRS instrument, so around 11 and 12 microns. And so there is a standard land surface temperature product from Landsat that's available through Earth Explorer. It also includes an emissivity product that's ingested from the Aster product, in fact. It is similar resolution to EcoStress. It's natively at 100-meter resolution. Something that users don't realize, though, is that they do bicubically interpolate the data to 30-meter resolution to match the VSWIR data. Although that is a synthetic interpolation, it doesn't come in at an original 30-meter resolution. So, with 8 and 9, it's really useful because when you combine the 2 data sets, you get almost a weekly repeat. But it does come over at the same time every day. So 10 a.m., roughly about 10 a.m. in the morning, depending on your latitude. And so if you're looking at, for example, extreme heat, or you want to maximize, when you observe the maximum temperature in the day, it's not that useful. But nevertheless, it is a very well calibrated, very well geolocated instrument, and is really useful for a lot of users. And it complements EcoStress very nicely because EcoStress is able to measure the thermal radiance over the course of the diurnal cycle in combination with the Landsat data.
Okay, thank you very much, Glenn. Okay, I do have another question for you. Can you speak to any group that has studied chemical-induced vegetation stress with the EcoStress data? For example, dioxin, etc.
Chemical-induced
vegetation stress.
That's a good question. Let me take note of that, and I'll ask our group maybe at the next meeting, and see if there's been, we have a couple of guys who are more specialists in that field within the thermal infrared group.
Well, that sounds great. And so for this particular user or webinar participant, we should be able to follow up with you offline with some more information regarding your query. So the next question is, how can we sharpen EcoStress data to obtain field scale information?
Yes.
I see that Christine provided a link to a tutorial, but I think it would be helpful to address it further.
Sure. Yeah, I've been putting the links to our GitHub tutorial in there as well, and I see there's been a couple of questions on that, which is great. Yeah, we spent a good part of last year coming up with a data mining sharpening algorithm that uses a combination of either Sentinel or Landsat visible shortwave infrared reflectances to take the ECOSTRESS 70 meter pixel and sharpen it down to that 10 to 20 or 30 meter Landsat Sentinel scale. And it's primarily a machine learning model, but we train the model to understand what the correlation is between surface reflectances and the land surface temperature, pretty much, while still preserving the original measurement at that 70 meter pixel from EcoStress. And we have several examples of that. We have the full Python tutorial in our GitHub. So I highly recommend people go and look at that. And if you have any questions, you can also ask me. We have a number of other people here on Lab 2 who frequently use the sharpening tutorial, so they may have some more experience than me myself.
Well, I appreciate the feedback there. So with that, I think to stay on track with our time, we are going to transition to our next speaker for this afternoon, Eric Bolch, who is going to provide an introduction to NASA Earthdata, data access, and Openscapes cloud introduction. So with that, Eric, I am going to toss it over to you.
Okay. So my name is Eric Bolch. I'm with the Land Processes DAC. And so you guys have all heard a lot about the science behind these data sets and the various different applications, how they can be used. My talk is going to change gears a little bit. I'm basically going to go through like, okay, well, how do I find this data? How do I access it? How do I get it, download it, and get started working with it? And so first, I'm going to talk about a little bit about the NASA Earthdata organization. Then I'm going to go through like how do you get the data access, and then I'm going to give like a brief preview of sort of some of the workshop we're going to present tomorrow, where we've got a cloud Jupyter Hub instance, and we'll be able to actually go through some Python notebooks together tomorrow. So what is NASA Earthdata and the LPDAC? So essentially, NASA Earthdata is the organization responsible for archiving and distributing all NASA's Earth science data. Right now, there's about 129 petabytes. So if you're unfamiliar with that, that's 129 million gigabytes of data. And so all these data and the resources we produce are available for free. You can get them from the Earthdata website and through some other applications. And so in addition to just distributing that data, we also develop tools and resources to help people use it more easily. And I mentioned before that I was part of the LPDAC. That's the Land Processes Distributed Active Archives Center. And that's just one of several DACs that kind of fall under the umbrella of NASA Earthdata. We all have a different sort of data we're responsible for. Our focus is mostly on land-based data. And so that would be like ECOSTRESS and EMIT. The OB DAC, which is the Ocean Biology DAC, is responsible for the PACE data, which we'll also work with a bit in these notebooks that we walk through tomorrow. So all of the NASA data is being migrated to the Earthdata cloud. And so that is a managed commercial cloud environment that's part of Amazon Web Services. And what this does is do a couple things to help the user. So this is going to help reduce like latency, improve download speed. The scale that AWS has allows like some redundancy and better access to the data than we were previously able to provide through like our different on-premises locations. And there's some other benefits here. We have several different applications that run in the cloud, and this allows them to perform more efficiently, work faster. One example I'll talk through a little bit is the Appears application, which is a tool we recommend for working with a lot of the data from the LPDAC. And so another application that's part of this would be like the common metadata repository. And you can think of this is a big catalog that essentially serves as a table of contents, so you can find any data set that is an earth science related data set that we archive. So like within that, you would have like a scene, and then at a broader scale, you have all this other metadata information, like when was this image collected, when was it processed, all these sorts of relevant information, and they're not always tied to each. I'm sorry. There are a couple unique ones to each data set. So like you can find things like cloud cover percentage for different scenes for some data sets. And you can search this repository for all these data. And this is sort of the underlying system. But on top of that, we have things like Earthdata search, which I'm going to do a short demo of. And that's basically a graphical interface where you can search this catalog, find the data you're interested in, and you can search like spatially, temporally, and by some other key metadata. And then also, there is an API for CMR search. I'm not really going to talk about that today, but tomorrow when we do some of our Python notebooks, we'll use the Earth Access Python library, which is a wrapper for that API that makes it really easy to use when you're in Python. And so now I'm going to minimize this and kind of go through a bit of a demo here. And so for Earthdata search, let's see, I've actually got the link here. If anybody wants to follow along, it's here on this like webbook page. You can go to Earthdata search down here. And it's just search.earthdata.nasa.gov/search. And so this is where you can find any data set you're interested in. And so since we just talked about ECOSTRESS, I'm going to do like a search for ECOSTRESS. And you can here put this in quotes. Some data sets have like ancillary information from others. And so if you throw that in quotes, it'll make sure that you're getting all the data sets that are tied to a certain instrument. Here you can see there's a bunch of different options, bunch of different product levels. Like this is the tiled land surface temperature. We then have like a swath land surface temperature, various like, geolocation data, evapotranspiration. So you can see all of these data sets here. And so you could select one here, or you can go ahead and sort of refine your search to something more interesting. I know like one of the examples like Glenn talked about was like urban heat islands. So what you could do, like you could add a polygon or something over like a city. And I'm just going to draw a bounding box here. So you have this sort of toolbox on the right-hand side where you can search using different features. So like you could do a circle, a point, a rectangular bounding box, or a polygon. I'm just for simplicity do like a bounding box here. And so we'll be able to see that this is being applied to our search. And so like within these different products, it's refining that down to just this spatial area. And I'm going to go ahead and click on this land surface temperature to look at that so we can see how many results there are. And so like you can see here, there's 16,000 scenes within this area. And you can also see here that there are multiple tiles since this is the tiled product. So a couple things we could also do here, since we're talking about heat, like we could filter this temporally. So like you could do a time frame, like say you're interested in like the summer months. That's not what I wanted to do. Anyway, some summer months here. And so we could select this for 2020, just like through the end of August or something. And then one thing we could also do here is we could decide, like, we have this range we're searching, but maybe we want to just do summer and do a time series over multiple years. So you can use this recurring time range to change this. So we could do like up to current from 2020. And so, like, if we go back here to our land surface temperature and emissivity, we can see that this has filtered us down. I think before we were at about 16,000 scenes. Now you're at about 3,500. And then there's other things you can do to filter. You can add like a nighttime, daytime for ECOSTRESS. Some other information like the orbit number, which is in the file naming convention, things like that. But one of the more handy things you could do is you can use this granule ID search. And this will allow you to be able to search by things like tile. And so, like, if we hover over this, you can see that it corresponds to one of these entries here. And so we can kind of figure out what tile we want. Say, like, we want this middle tile here. You can scroll down and see that is tile 11 SMT. It's just in the name right here, 11 SMT. And so we could refine this for a specific tile, using asterisks here as like a wildcard. So it'll find anything that has that in the name. And so here we've got like 400 tiles over just this region of Los Angeles here that's within our bounding box. And so, like, after you have these results, like, there's a couple things you can do. If you want to preview like a couple scenes, like, you can download the granules here. For this data set, there's several assets associated with each granule or scene. You have like a water mask, a cloud mask, some geometry information, the land surface temperature, and then the emissivity. And so you could download any of those, or you can add this to your project. So project is sort of like a list of things that you can group together. And I can show that, although I forgot to log on at the very beginning. So here, what we can do is we can log in. And so this will prompt you for your credentials, but this will allow you to save things like your project. So here we've got like our 400 scenes. We can click this add button to add all of them, or we can just select like an individual one and add it to the project. Additionally, we can go ahead and download everything. I'm going to remove, and I'm just going to add everything here. And then go for the download. And so that when you actually click download, it's going to give you some options and give you some file information. So you can see there's 400 granules, and there's an estimated size of 4.4 gigabytes. And so you can download those by just clicking this here. And then since we can save this as a project that we can get back to later. But if we click download here, it brings us to another page with some options for how you can download or get the data. So here, it prepares like a download where it'll send all of these to your browser. But if you're like me, you don't really want to send 400 files to the browser. Like, you want to probably do something with this in Python or programmatically. So what you can do is you can actually copy all this information here. And this is basically the URLs to every single scene. Or every single scene and asset. So you've got all of that here you can retrieve. And you can also save that. So like, this will export this as just a TXT file that has this list of scenes that you can interact with whatever software you'd like. One more thing I will mention is we talked about how everything is now in the cloud. You can get these S3 links. So if you have a computing instance that's also located in AWS US West 2, you can utilize the S3 protocol, which will let you work on this data directly in the bucket. And that'll significantly improve like the speed of the access to the files. And so you can do the same here. You can copy, save, work with this however you'd like. And so hopefully that just gives like a little bit of insight into some simple ways you can work with Earthdata search. I will mention, since I did it before, you can search this data. All this stuff is free of charge, but you do need a NASA Earthdata account to download that. And maybe I can get someone to provide that link in the chat so you guys can set that up, because you will need that tomorrow if you're planning to attend the workshop. One last thing I will also talk through here before I mention, or before I give a little preview of the Jupyter Hub, is I do want to mention Appears. So we have a service called Appears, and what it does is it subsets your data for you. So say you want to work with like EMIT or ECOSTRESS data, and you have a set of points. You can provide those points as a CSV. The Appears application will extract all those points for each data set you specify. So you can select what layers you want. Like maybe you just need the cloud mask and the LST for ECOSTRESS, or maybe you have a series of bands you want from EMIT. And since EMIT has 285 bands, you only need a couple of those for whatever analysis you're doing. You can just pull those bands out, and Appears will return that to you as a CSV file. And so it really helps minimize the amount of data you have to work with. This little figure here about data volume, we typically reduce volume by about 99% on every Appears request that's made. And you can also do this for area. So if you have like a certain polygon or shape file, you can upload that to Appears and get a subsetted data set. It's very handy for building CSV files that you can use as like an input for some sort of classifier or something like that. It's a really handy tool. And lastly, I'll also mention that we have a ton of different GitHub resources. We have resources for Appears, and I didn't mention it, but Appears also has an API, so you can interact with that through the API or Python. Tons of examples for working with these various data sets at these links. And then lastly, I will go back to the webbook page. And here, I'm just going to give a brief preview of like the cloud workspace. So there's there's some setup instructions, and really the only thing you need for the workshop tomorrow is going to be an Earthdata login. And then you can click this here, and this is going to open the Jupyter lab for you. Now I already have like a copy open, but when this loads, like you'll be prompted to like sign in, and we'll give you the credentials to sign in tomorrow. But after you're here, you've got your little cloud workspace that has like a command line that you can work with, and you can also open like Jupyter notebooks. So just quickly, like as an example, I'm going to go ahead and just clone the repository we're going to work with tomorrow, just to show that real quick. And so within this interface, you can work in the terminal, and then over here on the left, you've got your directories. You can look through like a normal structure. And then up here at the top, there's a couple menus, and I'm going to maybe hit some of the important parts. the first thing I'll talk about it here is like this is the control panel. So like in the file menu down at the bottom, you have this control panel. And what this does is this allows you to stop your server. And we just ask that everybody, like when they're not using this, that they shut down their server. Because it does cost money to run these in the background, and we appreciate everybody doing that for us. So here, like we can do something like we can navigate into this repository that I downloaded, and we can go in the Python folder. There are a bunch of notebooks that we'll get into tomorrow, but we could open one of them, and then you'll be here where you can actually just run the notebook in this instance, and kind of learn how to work with the data. And so like all of these notebooks will kind of cover like how to find data, how to work with it, and I'll do a more thorough explanation of working in this workspace tomorrow. And maybe I'll go ahead and end it there, and we can address some questions.
Oh, okay. So I do have a question. Are we going to need something else besides Earthdata user ID and password for the workshop?
No. So basically, after you have your Earthdata account, you'll use that to basically access the data. As far as the Jupyter Hub, that's going to use a different credential. And so we have like a common set of credentials that we're going to provide to everybody tomorrow. And you'll just be able to log in. We ask that you use your email address. And then we have like a shared password that'll work for everyone to easily get people logged in.
Okay, thank you, Eric. Take a look here. Okay, the hub requires credentials that will be shared tomorrow. Several people have been asking about whether or not this presentation is being recorded. Yes, it is going to be, it is being recorded. However, it does take a few days for the recording post-processing and to get it uploaded to a YouTube channel. And let's see, when that is completed, what I will do on my end is send an email to all webinar participants and to those registrants who are unable to attend, with a link to both the GitHub repo, which houses all of the presentation slide decks, and also Jupyter notebooks that have been used, as well as a link to the recordings. Let me check the chat, and let me actually also check to make sure they haven't missed anything in the Q&A. I'm looking at any. Thanks for your patience here. Let's see. Just making sure here. I don't see. Okay, I do see something. What can Earthdata do that you can't do through Google Earth Engine?
Okay. So maybe that's a little bit of a complicated question. A lot of things that you can do with Earthdata, you can do in Google Earth Engine, although Google ingests the data from us, and they do reproject to like their own kind of custom tiling scheme, which is probably okay. But like for the formal copy of the data, like I would recommend working through like NASA Earthdata or Data Search. If you're, I'm not saying there's anything wrong with Google Earth Engine. Like it's a great tool. But they do make minor changes and stuff to the data so they can stack it. It'll work within the GE framework.
Okay, and then I have a follow-up question. Let's see, hold on a second. What emails will be used to log into the cloud workspace?
Just like whatever email you want. There's not really a username required other than that like you provide one. So like I guess like there's not an official list or anything. Like we just ask that you provide your email. That way we can stay in touch if you need help with something.
Okay, thank you. So I'm not sure. I don't think I've missed any questions that are specific to your content, Eric. But I was wondering if let me do a double check before I say that. Someone may have just entered something. All right. Will we go over how to access AWS S3 buckets for Earthdata? I am new to this process and it would really help me in my projects.
So we actually aren't exactly going to talk about that tomorrow. We have some examples in the tutorials, and we can find a link and get that to you. Tomorrow, or like the content for this workshop has kind of been designed to be cloud agnostic. So like you could use it if you're in any cloud or on your own personal computer. But we do have some tutorials specifically for doing S3 work with the NASA data.
We do, and I once we're finished with this, I'll try to find some links. There are some posted on the Earthdata website as well that could be referenced. Okay, so let's see. I did see another question. Can we have access to multiple images through AWS S3 bucket? Recently, I tried, and it returns an error.
Maybe you can provide some more specifics. And you know, I can, if you want to put in a support ticket, like we can try to get you a solid answer. Maybe you can send like your example and stuff. And we'll take a look at it.
That sounds really good. If it's okay with Africa, Eric, I don't see any further questions for your content. Would it be okay to go back and revisit some of the questions that have not been addressed yet? Since we have, what do we have? I think we only have like 2 minutes, so maybe one question.
Sure, go ahead.
I think it's a question though. Let's see. The questions are getting quite long here, so let me prioritize questions. Thanks for your patience, everybody. Just take just a quick second. Well, it looks like Christine weighed in on this one. Let me go back to the questions. I feel like I saw a question that I wanted to ask that we had not addressed yet. Okay. So I do see in a question, what is the page we need to use to shut down the Jupyter server? I'm not sure if that's something that you can easily rattle off here.
I mean, I could share my screen again real quick, if that's helpful.
Sure, that sounds good. I'm just looking through as you do that.
So when you're in the hub, to shut it down, like if you go to the file menu, down here at the bottom, there's a hub.
We're not seeing your screen. Yeah.
Okay.
That's okay.
Just kidding. There we go. That should be working.
Yes.
Okay. I didn't click OK. Anyway, here at the file menu here on the Jupyter Hub, there's this Hub Control Panel option here. So if you click that, you can see here this red button, Stop My Server. And so whenever you're done working on it, you can just click that Stop button, and that'll stop it. If you want to relaunch, I mean, you can. You would just go back to that same link again.
All right. Thank you very much. And I'm just scanning through to see. I don't see any questions that I've missed. Yes, I do. All right. So up in the chat, well, then we really need to transition over.
Yeah, I think that just
let's go ahead and transition over to our last speaker for the day. We're going to turn it over to Emil Sherrington. Jennifer Charrington, who is going to provide a GEE platform overview. So with that, let me mute myself and toss it over to Emil.
Yeah, thank you so much, Jennifer, and thank you, Africa. Hi, everybody. Good afternoon, or I guess, or good evening, depending on what part of the world you're dialing in from. My name is Emil Charrington. I work for the University of Alabama in Huntsville, and I support activities at NASA Marshall in NASA's Earth Action program. I'd just like to, again, say thank you to Dr. Africa Flores Anderson and the other colleagues who gave the really great presentations. And I guess I'm closing everybody off for this webinar just with an overview of Earth Engine, which we're going to be using tomorrow for some of the exercises. And so I just wanted to point out that there's a QR code there. I also created a separate GitHub page that has links to these materials, in addition to the links that you'll find in the page that that Eric and Masa have so kindly put together. So that all said, I just wanted to start off with a small disclaimer. And so just like Eric said just a few minutes ago, we consider ourselves platform agnostic. And so I'll be showing you Google Earth Engine. However, just like to note that it is a commercial product with specific terms of service. You are free to use it or other commercial platforms like Amazon Web Services, Microsoft, etc. That out of the way, just I guess the overall thing for the next little while. Hopefully with this presentation, you get an idea of the basics about Google Earth Engine, and I get to show you a little bit to the what's called the Google Earth Engine code editor, where we're going to be doing data visualization, etc. in the presentations tomorrow. And I also would like to say that I just assume that of the 300 plus people in this webinar, that many of you are already familiar with Earth Engine. And if not, this will just be a quick overview again to prep you for the exercises. Tomorrow we'll be working with PACE and EMIT and other data sets. So in terms of an overview, for those who, again, might not be so familiar, what is Earth Engine? And again, I've borrowed slides from other colleagues of mine. Earth Engine is a free web-based image analysis tool, and it facilitates scalable and shareable image analysis through this interactive development platform, the code editor that we are going to be using tomorrow in exercises with Africa and myself. The other thing about Google Earth Engine, similar to what we're going to be seeing with Eric and colleagues and the notebooks tomorrow, not in Earth Engine, is Earth Engine facilitates work with big data. So analyzing and visualizing the data, and at least the tagline from the colleagues at Google who developed Earth Engine is that they designed it for use by scientists and not software engineers, just simply because for those of you who've been working with Earth observation data, geospatial data for a little while, you realize that sometimes working with big data sets can be challenging, and sometimes it does require a bit of expertise that we scientists might not otherwise have. That said, Google Earth Engine does make it easy and enable non-traditional users to be able to interact with these different types of data sets. And the idea that they had when they developed the Google Earth Engine 15 years ago, back in 2010, was that it could be focused on society's big challenges and reduce the time spent in analyzing the data, or reduce the time spent in processing the data so that we could focus on the fun stuff of analyzing the data. The other question you probably have is, what does it contain? And so similar to Eric talking about the, I guess over 100 petabytes worth of public data available through the LPDAC of NASA, Earth Engine itself has a public data catalog that's being updated daily, and it contains something around 90 petabytes worth of data, or at least that's the latest information I was able to get. It has data in terms of weather forecasts, climate models, a number of analysis-ready data sets, a number of the data sets that we've talked about using, data from the full series of the Landsat series of satellites, MODIS, Sentinel-1, Sentinel-2, other data sets, process data sets like digital elevation models, land cover data, surface temperature, et cetera, et cetera. And again, the neat thing is just kind of, and as we'll see shortly with the code editor, through the code editor itself, there's a little search bar that you can easily find, what's there in terms of the public catalog. And so again, and maybe this slide I needed to have updated. When we put there that it has over 50 years worth of data, we're referring principally to, for instance, the data that comes from Landsat, data from 1972 to present, but again, other types of data that we're using. And to borrow Morgane's earlier slide, just wanted to highlight of some of the different satellite missions that are part of what's called NASA's Earth Fleet, such as data from GRACE, data from SMAP, the Global Precipitation Mission, Terra Aqua, Suomi, JEDI, Tempo, etc. A lot of those, as highlighted in yellow, are already in Earth Engine. And the one that I've highlighted in green wasn't in Earth Engine before. And tomorrow, one of the things I'll be discussing is some work that we've done here at Marshall in, I guess, putting some of the PACE OCI data into Earth Engine. And we have an exercise showing that. And again, really thankful to the support from Morgane and the PACE team at Goddard for this type of work. And of course, EMIT is also there, as has been asked about in the chat. Just again, some filler before I show you what the code editor looks like. As Eric was also kind of getting at, Google stores the data in specific formats that are called image collections, which I guess are similar to when people talk about, stacks of imagery or data cubes, which facilitates cloud processing and distributed computation of the data. And just the really neat thing, which you're able to perform analyses on extremely large data sets. And so, we users were able to do things at, say, a global scale or on finer scales, et cetera, depending on the type of data. And at least for me, I think one of the even neater things is via the same code editor, it also provides a really simple way of you're working on scientific code, and you're able to click the little get link button and easily share that with other colleagues who can then continue working on that, send it back to you and view it, etc. And I guess there with that graphic there, just kind of showing that it's, leveraging different clusters for computing that Google has, and essentially by kind of breaking up these different workflows, then putting it all back together. The other thing about the code editor that we're going to be seeing in just a little bit is that it allows for us to not just map and plot data, but also has an interface for printing results. And so, for instance, you can, similar as you can do with desktop GIS systems, say click on a point and interrogate the values, but also plot things like time series of values or spectral signatures. It already contains a library of different algorithms that we might be interested in using, gives you the building blocks to create your own workflows. And some of that we'll be seeing with regard to the hyperspectral data that's there. And as mentioned before, saving and sharing that data. And they also provide you with example scripts. There is a GEE developers forum or a Google group that, people are always, posting questions to or consulting for code, assistance, etc. And that's neat. And I guess also that I believe the latest statistics are that there are something on the order of 20,000 active monthly users of Google Earth Engine. How to use it for the exercises tomorrow, we're going to be looking at the JavaScript API, what's called the code editor, which is, again, really easy to use and to see your results. But there's also a Python API. Other colleagues in the community, like Professor Kusheng Wu from University of Tennessee, who developed something called GMap or GEMap that allows you to easily interact with the Python side of things and work with Jupyter notebooks, etc. And whether you're using the JavaScript API or Python, Earth Engine also facilitates apps for easily sharing what you're working on with people who don't have access to Earth Engine. That all said, what does the code editor look like? I would encourage everybody, if they have not already followed the instructions that Jennifer shared along, to, of course, register, but also check out, to be able to make sure that you're properly registered, you'll want to go to the link that's listed there above, code.earthengine.google.com. Hopefully, one of my other colleagues, perhaps Africa, could also just share that link in the chat, or of course people who might be following along with these slides. Check this out. Thank you, Africa. And when you open that up, and of course, if you've opened that up and you find that you cannot kind of get in because you haven't registered a cloud project, in the next few slides, I'll also walk people through that process really quickly. But the main thing with the code editor is, again, it's this interactive development environment where basically you have, and you can resize the different windows and consoles, etc. But on the bottom, a window where there's a map viewer for the whole world, and when you generate results, you can see them on the map viewer. Or and let me, I guess, go through this and apologies for the resolution on the image. In the top left part that says scripts, and these are the scripts, the code that you'll be, script manager, as it says there, the code that you're going to be writing or accessing. There's another part there that says docs, which is the documentation for the API that contains information about the different algorithms that are there. There's a part that says assets, or data assets that you've saved, or files. The middle section where we're really working, where we're putting in our codes, or writing our scripts, etc. But also the links to get scripts, to share scripts with other people, save them, run them, etc. And then on the top right side, an inspector, which is similar to the I button that you're going to find in ArcGIS or QGIS, that will give you information about the pixels you're interrogating, like the location, a console that will display certain information that you might be asking for, or for instance, if you're printing spectral signatures, where you're going to see those, and a tasks button in the event that you say export data to Google Drive or Earth Engine for saving, you're going to see that stuff in there. And of course, in the map viewer, tools for drawing, zooming, and also turning on and off layers. That all said, and again, the proof of the pudding is going to be tomorrow when we actually do the walkthrough. Lastly, on this, I just wanted to mention that there's this large public catalog of data sets, the Earth Engine data catalog, that's maintained by Google itself, and where they're again ingesting different data sets. And I know that there are plans for ingesting some of the other data sets that people have asked about. And then lastly, in addition to the public catalog that's maintained by Google, a good friend of mine, Sam Roy, maintains the awesome GE community datasets, which is a community data catalog where you can essentially put a request for a public domain dataset to be ingested. And speaking of hyperspectral, Sam recently ingested the Planet Tanager 30-meter data that was just released on Friday. Also ingested into that. That said, and since I have roughly 10 minutes left, let me just escape out of this and pull up the other presentation. Just wanted to also, again, for the benefit of people who might not yet, who you've clicked on that code editor link and you find that you have an issue getting into Earth Engine. Let's say you clicked on that link and you come up with a window that looks just like this. It says, "Welcome to Earth Engine." It gives you options of either you want to register a cloud project or you're already authorized for one. I'm assuming that some of the people who've signed up for this, you're going to get this window, and so basically you're saying you want to register a new cloud project. So you click on that, I said there. And one thing to mention is, if you're doing this through an institution, particularly like a U.S. government institution, you might have issues doing so, because government institutions here in the U.S., for the most part, block people from creating Google Cloud projects. And so I would recommend to everybody, and there have been a few emails that have come in through Jennifer. Thank you. The recommendation is, if you have a Gmail account, and I assume everybody already has a personal Gmail account, you would want to log into Earth Engine with your Gmail account, and then when you get to this window, click that register button, which will then allow you to create a project. And the first thing you're going to want to do is give a name to the project. In this instance, because we're doing a NASA training in July 2025, I call this one NASA Training 2025-07, but you can put any name that you want. And also to mention that after you put that, you shouldn't have to specify an organization. If your options come out slightly differently, like it's asking for a location, again, it might be because you've signed in not using a personal Gmail, but with another type of account. But again, if you get to this window, etc., then the next thing you'd want to do is click create. And after you've created, you should then be able to, you'll get to a page like this that asks you to register that project. We're going to click that register button. And again, if I'm going too fast through this, the links to the slides are on the page that Eric has shared and put together. So you can walk through this in your at your own pace. That said, after you've registered your project, you will come up with a prompt that asks you either to register for commercial use or see if you're eligible for non-commercial use. Because we're doing this training webinar that qualifies for non-commercial use, so we're going to want to hit that get started button at the bottom. There you're going to have to specify the type of organization, and it does give an option for Earth Engine trainer or trainee. I assume since those of you who are being trained, you're going to want to select that option. Hit next. It will ask you to check your non-commercial eligibility, and you can then select that you're a participant. We can put in the different dates for the training, or you could maybe spread it out a little longer if you want to continue testing, I guess, further from this. But in this case, I had specified today and tomorrow as the start and end dates for the training. I hit next, and it says, based on the answers I provided, I'm eligible to continue with non-commercial use of Earth Engine. After that, a next button pops up. We click that. Asks us to choose a plan. However, as it says there, since this is non-commercial, there's no pricing plan, so we can click next again. It will ask us to describe our work. I think the main one with the asterisk that is required is the one that says, will you use Earth Engine for any of the following? So you're going to want to select one of these. And as an example, for those of you who might be interested in, say, PACE for ocean or coastal related things, you could pick oceans, ecosystems, and conservation. There are other options as well that you might find more appropriate. Select one of those options, and then click OK. You're going to then see that next button again. You click that. You're going to hit, after you click next on that, you're going to have a summary. The summary looks good to you. You can click that register button. And then one more prompt is going to come up indicating that for Earth Engine to work, that the API needs to be enabled. On the bottom right, you're going to see enable. So click that enable that I've highlighted there for you. Click enable. And then with that, in that same tab, you should see information about your project, that it's now registered. And so with that, you're going to be able to go back to the tab that has the code editor. You might have to refresh that tab. When you get there, it will still ask you to choose the cloud project that you're going to use. In this case, I have the option of picking the NASA training that I just registered. I do have some other projects there because my account has multiple ones, but for most people, it should be the only project that you have. You're going to want to click that, then hit select, and then voila. With that, you should now see a window that looks just like this. And the final step of this, and then going back to, since we're going to be working with Earth Engine tomorrow, specifically for PACE and also for EMIT, I've added just a few other steps there for something that we're calling the PACE OCI Toolkit. I should also mention that I'm one of the PACE early adopters. And so we put together this toolkit where essentially we were the ones who loaded in a lot of the PACE OCI but land focus data into Earth Engine. There's a link there to the GitHub repo that describes what that is. But really what you're going to want is either the link that's here, which is just bit.ly /g_repo_pace_OCI, or you could scan this over here. And again, if I'm going really quickly, and I know I only have a few more minutes, The slides are in the link that Eric shared. When you click this, it ultimately will just pull up a code that says accept repo. And I just figured that a bit.ly link is shorter than typing all that stuff out. It will ask you if you want to add this repository to your workspace. You're going to say yes. And then when you do that, you might not see anything there. And so you might want to, if you don't see anything, you're going to want to hit that refresh button in the top left. And when you do, under Reader, you're going to see it now says users/serverbz/paste OCI. And that is this repository that we're going to be using tomorrow. And I guess with that, I've basically given you a quick walkthrough of Earth Engine, as well as how to get through the steps of registering for a cloud project. I think I can stop sharing, and I think I saw a question there from Jennifer.
A question from me? There is a question. Okay. So the question was, so the question is, the user is asking, register for a new project, or we are authorized to work in an existing cloud environment?
Yes, apologies again for going a little fast. It's register for a new project. And let me...
Excuse me, existing cloud project.
Yeah, no,
it's an environment, but yeah.
Yeah, no, it's definitely, I want to register a new project, the first of the two options. And let me, just for the benefit of folks, maybe I could just post it in the chat. These slides, again, they're also on the vitals page the page that Eric set up, but also the specific slides that I've been looking at. I just posted the short link there. On the third slide, again, it's the fourth slide, you want to register for a new project. And
thank you very much, Emil. I did see another question, but it looks like the webinar participant answered her question. All right, so the next question is, what if you already have your DEE account? Do I need to register for a new one?
No, you don't. You can just use one of your existing projects, because the main thing is just making sure that you're able to get in. And so particularly for new people, if you haven't created a new cloud project before, essentially the registration step kind of is like a block. And so until you specify a project, you can't get into the code editor. But if you already have an account and have a project, then yeah, you don't have to create a new project all over again. Thank you.
Okay, thank you. And I do see a question from a workshop, someone who just has a generic entry here. So we will be providing a log of the Q&A at a later point in time with, all of the questions that were not responded to, actually, addressed with a text response. And then I would not be providing the chat log which includes PII for our webinar attendees. Certainly that can be stripped out, but since the chat is private between the hosts and the panelists, that is not something that we would send out to all attendees, just from a privacy perspective. But feel free to email me if you have specific questions, since I don't know who, until I look at the logs later, who this is. I'll put my email address in the chat. All right. And just checking really quickly. Don't forget to register for day 2. We did put the link in the chat. We did have, we're at 5 o'clock, so hopefully there'll be an opportunity, Africa, to address some of these questions that could be answered easily during a Q&A, like a carryover from today, tomorrow. I don't know if the time, I'm just looking at the schedule now, if there's any time for that kind of thing, but perhaps during the break, those that do not require an in-depth follow-up. I'll try to outline those before tomorrow, and if we have time, it'd be great to try to address those.
Yeah, we can try for sure. Thank you so much, Jennifer. And I think that many of the questions that perhaps haven't been addressed will be resolved tomorrow while we
Perfect.
walk through the tutorials as well, because that can clarify a lot of the questions that may still remain. And because we have a lot of content for tomorrow, so we make sure to have the log of all the questions and address each of them the best that we can to send them later as well.
Okay, that
yeah.
sounds very good.
And I
Great.
want to thank all the presenters and all the participants for the great questions, and pass it to you. And thank you so much, Jennifer, for hosting the event and being so flexible with all of us.
Well, of course. And I will see you all tomorrow at 1 o'clock Eastern time.